I wanted to check if you hear me.
Hello, yes, very well.
Thanks. Hi, everybody. I would propose to wait a couple of minutes before everybody will connect. And yep, so let's wait 2 more minutes before we start. So I see that people are still connecting, but let's probably begin our third day, our third plenary session for the day. So I promise you it will be pretty interesting because we're going to talk about how I use Python in neutrino experiments and astronomy, as well. Interesting talk about the LHCb experiment and their usage of Python ecosystem. We'll touch a bit basis about how to use Apache Spark for physics analysis and with some live examples. And as well, we will talk about how to use coffee analysis framework together with WorkQ for distributed analysis. So I would welcome to share slides and to start the first talk. Just Migella, sorry, Mingenda.
Migenda.
Migenda, thank you. And yeah, so please go ahead and tell us a bit more about your interesting topic.
Okay, excellent. You should be able to see my slides now.
Yep, we see it.
So let's get started. So I'm here to talk about the supernova early warning system, SNOOS for short, and some Python software we're developing for studying supernova neutrinos. You can see here the only supernova that's been close enough that we actually detected supernova neutrinos, the famous supernova 1987A. Now, I realize most of you are not from astrophysics, so as a brief intro, supernovae are explosions of massive stars, and they leave behind a neutron star or a black hole. And as part of the explosion, a lot of chemical elements, things like the oxygen in your lungs, or the calcium in your bones, or the arsenic in your favorite Agatha Christie novel. All of these chemical elements that are essential for life are thrown out into the universe. So we are all made out of remnants from these supernovae. And these are absolutely magnificent explosions where this one single star, like in the picture on the right here, can shine as bright as a whole galaxy consisting of billions of stars. And yet the largest part of the energy is not emitted as visible light, but in neutrinos. And detecting these neutrinos gives us unique insights into the astrophysics, into particle and nuclear physics, and all of this under extreme conditions. We can test general relativity, we can, so we have access to a wide range of different physics. Now, the problem is that because neutrinos only interact weakly, we need a nearby supernova, basically anywhere within our Milky Way, to detect these neutrinos. And those happen quite rarely, only about 1 to 3 times per century. So the next galactic supernova will be a once-in-a-lifetime event, or at the very least, a once-in-a-career event. So our goal is to extract as much multi-messenger information as possible, from neutrinos, from gravitational waves, but also across the whole electromagnetic spectrum. And now, because neutrinos are emitted right in the moment of explosion, whereas the electromagnetic signal is only produced, once the shock wave breaks through the outer layers of the star, the neutrinos are actually emitted minutes to hours before the light, which means we can build a supernova early warning system with neutrino detectors. So once those detectors see something that's probably a supernova, we can alert astronomers and tell them to get their telescopes ready, because the shock breakout burst that they are looking for is on its way. Now, this idea is quite old now. It was started when I was just in kindergarten. And the original SNOOS 1.0 has been running in automated mode for almost 20 years now. Today, there are 7 participating detectors all over the world, including IceCube here on the South Pole. But about 2019, we started asking ourselves, what would SNOOS look like if we were to build it from scratch today, with all the progress on multi-messenger astronomy that we've had in the past decades. And so the result of that is a white paper that's published here. And this new design, SNOOS 2.0, includes a bunch of new features. In addition to just sending an alert with basically detectors saying, hey, I've seen something. And then if multiple detectors see something within a 10-second window, we send out an alert to the world. We can do many more things. We can reduce the alert threshold. We can try to get pointing information to figure out where approximately on the sky this supernova is. And we can work closely together with astronomers to develop a follow-up strategy and much more. So with all of this, we needed to build a whole snooze software stack from scratch. And I want to go through that here on this slide. So we've got various participating neutrino detectors on the top left here. And when they see a couple of events in a short time window, which might be a supernova, they will send a message to the snooze 2.0 server. So this would be an alert, but they can also send heartbeats, basically just to confirm that they are online, they're operating as expected. And in principle, we could also send commands to, for example, measure connection latency or stuff like that. Now on this central snooze server, we've got various analysis tools constantly running, which look for coincidences between these experiments. And if there is a coincidence, they try to triangulate from the arrival time of the signal at different experiments, where in the sky is that supernova. And they could look for more advanced things like, is this a supernova that formed a black hole, which might be visible from the neutrino signal. And now when it detects something, a likely supernova, it will take all this information it gained from these analysis tools and publish an alert, both back to the participating experiments, in case, for example, one of the experiments had low statistics and wasn't quite sure if this was a real supernova, but also out to astronomers, to gravitational wave detectors, and to the general public. And there's actually a mailing list which you can subscribe to right now to get an alert from snooze. Don't worry, it's a very low traffic mailing list. I think we haven't had a single alert in the past 17 years. But so that's a kind of online messaging system. And then in addition to that, we developed some offline simulation tools to deal with supernova neutrinos. And these are used to develop many parts of the online system, like developing some of these analysis algorithms running on the server, or setting alert thresholds for experiments, stuff like that. And now across this whole tool chain, we're using Python basically at all stages, right? We're using it for the pub sub clients here to publish messages or to subscribe to them. We're using it for the real-time analysis tools running on our server. We're using it for the offline simulation tools, and I will demo these on Binder in the later half of the talk. And then, of course, many of the participating experiments and many of the subscribers, like astronomers, probably use Python in many of their internal tools as well. But that's, of course, beyond the scope of today's talk. Now I want to go through all these different steps of the tool chain here, starting with the publish subscribe mechanism in red. And for that, we have developed a collaboration with SIMA, which stands for Scalable Cyber Infrastructure for Multi-Messenger Astrophysics. And this is a project funded by the National Science Foundation in the US. And they're working with IceCube, the neutrino detector, the South Pole. They work with LIGO, the gravitational wave detectors, and others. And the first product they've developed is called Hopscotch. And this is a platform for handling real-time data streams for multi-messenger applications. And Snooze and SIMA started a close collaboration in the summer of 2020. For Snooze, we were interested in this Hopscotch system because using it meant that we wouldn't need to implement and maintain all the underlying infrastructure, things like identity management, authentication, the publish subscribe mechanisms, and so on, right? That's not what we're good at. we'd like to focus on the supernova specific parts of the stack. But then for SIMA, on the other hand, the reason they were interested is because they had just developed this early prototype of hopscotch. So for them, working with us was a real, really good opportunity to get some real world testing, to use this in a real application, get immediate user feedback, if their system works for us, or if there's, for example, missing features we need. And this collaboration actually went on for several months and worked so well that after it was all done, we wrote this paper on our experiences of this kind of collaborative software development between two different projects. And that's been published earlier this year. Now, in the time since, we've developed these snooze publishing tools on top of Hopscotch, and these let you either publish, as in the screenshots here, or subscribe, both from Jupyter Notebooks or from the CLI. And you can see here the message schema for some of these tiers. For example, for the simplest, for the coincidence tier, we send an ID, we send the detector name, of course. We send the machine time for the offline, sorry, for the time at which the detector identified this supernova trigger. And we send the neutrino time, which is the starting time of the neutrino signal. Then we also have this meta field, which in this case is an empty dictionary, but could include additional keyword arguments. And we have a schema version to maintain compatibility if, for example, the server and the participating experiment don't update their software at the same time. And these screenshots here show the subscribe functionality. You can see that's also quite short. And you can even give it a custom script that will be executed whenever you get an alert. Right. So this could do something like interact with your Alexa, for example, and have it speak up whenever you get an alert. Next up, we have the real-time analysis tools running on the server, and those are all publicly available on GitHub. Right? There's things like the coincidence system, which just looks for coincidences in a 10-second time window. We've got a heartbeat handler, which reacts to experiments sending heartbeats to figure out which experiments are currently online. And we've got this software called SnoopDAG, which uses a directed acyclic graph built from a lot of different plugins that can, for example, estimate the distance based on the number of neutrino events, or triangulate the direction based on the arrival times of different detectors. They can do, if we don't just send the initial arrival time, so the start time of the signal, but if detectors send the whole time series, they can do time series matching between different detectors to get a more accurate kind of time difference. And they can then compare this direction estimate we get from that with the distribution of progenitor stars in the galaxy to figure out, especially for close supernova, individual progenitors that might be the source of the neutrinos. Right, so we've got a lot of these tools. Too much to talk about here, so if you're interested, I would encourage you to look at these on GitHub yourself. And then finally, we've got this offline simulation software. And this is mainly in a tool called Snoopy, which does kind of three key things. First of all, it offers a unified interface to hundreds of supernova simulations. Because there are many groups around the world running computer simulations of supernovae to kind of figure out what neutrino signal we would see. But those all use different codes. They use different output formats, different time binning, different energies binning, and so on. So Snoopy gives you a simple unified interface to access all of these. Then, between neutrinos being produced in a supernova and being detected on Earth, a lot can happen. Right? Neutrinos are famous for oscillating. So even if you emit electron neutrinos, they can turn into muon neutrinos before they arrive on Earth. So we have this large library of different flavor transformations that relate the produced neutrino fluxes to the detected ones. And then finally, we have a Python interface to snow globes, which describes detector properties and which lets you go from the neutrino flux at your detector to actual event rates in many different neutrino detectors. And something I want to emphasize here is that the first two, this unified interface to supernova simulations and the library of flavor transformations, those two are available to import from your own code. So for example, I'm the developer of an event generator called SN Tools. And I've last year started to include snooze as a dependency in SN Tools to get access to many more supernova models and flavor transformations. There's another software called Asteria, which was developed by IceCube, which does a similar thing. And then in the last year or so, we've increasingly seen some groups outside of snooze start to use Snoopy in their papers. So for example, simulations groups that run a supernova model and want to easily see what signal this would leave in various detectors. But I think instead of talking about that, it's easier if I give you a little demo. So let me switch to sharing the binder window. There we go. So this is a demo notebook showing some of the features of Snoopy. And you've got links here at the start with a GitHub repository, the Read the Docs page. And there's two publications on Snoopy. One is in the Journal of Open Source Software, which was a review of the Snoopy code itself, and documentation, unit tests, stuff like that. And then there's this paper here in the Astrophysical Journal, which focuses more on the underlying physics. Now, to start with, what we'll do is we will download some sample data files. Snoopy actually includes data files from dozens of different model families, hundreds of progenitors in total. And here we will use two of them, one by the Nakasato group and one by Bollig et al. By the Garchin group. Come on. Got no kernel. There we go. Okay. The dangers of live demos. So now you can see I've actually let me this into presentation mode. You can see I've downloaded them into this new folder here called Snoopy Models, which contain different files for the different models. In this case, for the Bollig model, this is a text file with tabulated data of time, luminosity, mean energy, and mean energy squared. And you might think, wait a minute, from the mean energy and mean squared energy, I cannot extract the full spectrum, which is true. So we have to assume some spectral shape to put these parameters in, and all of that is included in Snoopy. So Snoopy does all that for you. And now, in addition to these model files, there's a README here, which includes the original source of these models, and there's also a notebook which demos these models and gives you an overview of what you can do. But back to the main notebook here. Okay, we've downloaded these sample files, and now let's start plotting them. And I'll take one model from Nakazato, one from Bollig. You can see here's an overview of the Nakazato model. So that's a 20 solar mass model with a certain equation of state and a certain metallicity. And now let's actually start plotting the luminosity of this model. And you can see here we've got this. So this is the first half a second after the explosion. And you can see this is, sorry, after the core collapse. And you can see we've got this initial neutronization peak here, a sudden peak in the electron neutrino signal. And then if we look at later times, let's say, if we look at let's say 5 seconds, if we plot this, you can see after this initial activity, the luminosity pretty much just falls off exponentially. So there's nothing very interesting happening here. So that's the neutrino flux as it is produced inside the supernova. Now let's go from this to the neutrino flux we'd actually detect on Earth. Now these can be quite different. And just to show one example here, I will use the adiabatic MSW transformation. And that's something that occurs because you've got this varying electron density in the star. And as the neutrinos travel from the center of the supernova to its edge, electron neutrinos are affected by those by that electron density, whereas muon and tau neutrinos are not. And so that causes some flavor transformation. First, I have these two helper functions to do some of the plots. And then, while this plots, let's actually look at this helper function. So what we do here is we take a bunch of energies between 0 and 60 MeV. We then get the initial spectra from the model at a fixed time and add all of these energies. So Snoopy does all the work behind the scenes to interpolate as needed by each different model, and then gives me these initial spectra. And then there's a second function called get transformed spectra, where I give it an additional flavor transformation, and it will then apply that to the fluxes. And then there's a bunch of plotting code here. Okay, now we've done that, and you can see here in the top line, you can see that from left to right, those are different time ranges. So maybe we'll just look at the left panels. On the top, you have the untransformed flux, and you can see you've got this very high electron neutrino peak, the solid blue line. That's exactly what we saw earlier. But now if we apply these transformations in the second or in the third row, you can see that this blue peak decreases dramatically. And instead the orange line, which is muon or tau neutrinos, that increases. So we see some of these electron neutrinos being transformed into muon or tau neutrinos. And you can see that the exact numbers vary, in this case, depending on the mass ordering. So depending on which of the 3 neutrinos is the heaviest. And then we can also plot the neutrino spectrum at a fixed point in time. In this case, at 100 milliseconds, and you can see, in this case, solid lines are untransformed, and dashed lines are transformed. So you can see, for example, the in this case, the electron neutrinos on the left and the electron antineutrinos on the right decrease, but their energy spectrum actually changes because of this transformation. So you can see, for example, that the dashed blue line here is much lower at these low energies, but actually is higher than the solid blue line, the untransformed spectrum, at higher energies. And we would see that in the detectable signal as well. Okay, so those are the neutrino fluxes at the detector. But now can we actually calculate the event rates we would observe in the detector? And that's what this last part of the notebook does. So what we do here, first of all, we pick a detector. In this case, we'll use a 100 kiloton water Cherenkov detector. So this is kind of similar to super Kamiokande or hyper Kamiokande. We'll use, in this case, a Bollick model. And we'll start with no flavor transformation. And then we'll just look at the first 1 second of the neutrino signal. So now once we've set these parameters, we can do the calculation. We do this in 3 steps. First, we actually integrate the flux over this 1 second time interval to get the number of neutrinos. We then multiply that with the cross sections for individual interaction channels and with detector smearing and detector efficiency matrices. And these are all included in this snow globe software I talked about at the start. And then we finally collect all of these into a data table. And you can see that took just 5 or 6 seconds, which is orders of magnitude faster than if you were to run the whole proprietary detector simulation for each experiment. And now let's look at this table we got as a result. You can see we have a header, which gives us the energy ranges, and then we have multiple interaction channels. In this case, inverse beta decay, electron neutrinos and electron antineutrinos on oxygen 16. We've got neutral current events, and we've got electron scattering. And then, of course, we have this data array, which has all the event rates. And so now we can go ahead and plot this. And you can see in just a few lines of code, we've actually got the total number of events. We've got the mean energy of these detected events, and we've got a plot of the observed event spectra in our detector, split up by all the different channels, right? And so if you, for example, want to build a new detector, you were to write a white paper for this, this is a standard plot you would put in there. And you can see we got this in maybe 20 or 30 lines of code, just defining our models, defining our parameters. Let's switch to a different detector, an argon detector, which is like kind of similar to Dune, that's currently under construction in the US. We have 3 lines to actually do the whole calculations. And then and then we have another 15, 20 lines or so to plot the event spectra for this different detector. You can see this looks quite different, this neutral current scattering on argon.
Just I want to just
weird.
Sorry to break your nice demo, just in case we are running out of the time and you already have 3 questions. So
okay,
take a look
Sure.
on Slido, and we probably
Sure.
will need to wrap with your talk.
Sure. So this was the last time. Yeah, I think we started a couple minutes late, so I'm sorry, I'm running a bit over. So yeah, Snoopy gives a way to access hundreds of supernova models in a unified way, has these many different flavor transformations, and an easy way to estimate event rates in neutrino detectors, right? So that's useful not just for us internally, but for pretty much anyone doing work with supernova neutrinos. And questions, of course, feel free to contact me on Slack or via email. And then let's look at the Q&A here. Let's see, first question by Eduardo. SNOOS exists since over 20 years, but multi-messenger astronomy is relatively young. Did SNOOS evolve for multi-messenger astronomy, and how? So yes, we did. We're almost finished building this new, we call SNOOS 2.0. And I had a little bit of that on the slides, but I also had the link to the SNOOS 2.0 white paper there, and I would encourage you to look that up. I'll put the slides actually in the repo along with the notebook as soon as I'm done with the talk. Another question by Graham Stewart. Does your community use Python mainly for convenience and familiarity? Do you need to take advantage of high performance Python, things like NumPy, Numba, etc.? And I think it's, so a lot of it is, yes, convenience, familiarity, also easy to get started for new members joining. And we're taking advantage of NumPy heavily under the covers of Snoopy. Numba, not currently. But yeah, definitely, for example, the all these matrix multiplications to get event rates in detectors, those are all in NumPy. And question by Oksana, how popular is the usage of JupyterHub notebooks for analysis in your community? I'm not sure I can give a representative answer there. So in our case, we have we use Jupyter notebooks heavily as documentation and as usage examples for Snoopy. I showed these notebooks that were included in each model folder, but we also have a bunch of other notebooks in the main Snoopy repository. Across the community, I think it's mixed, varies a lot person to person.
I see, thanks. And the last question, I would propose then to move to Slack.
Okay.
So we can even continue discussion there. So thank you so much, Just. It was like amazing. So hopefully, yeah, please go to the Slack so we could, just maybe other people has more questions. Sure. And yeah, thanks. Now we're moving to next talk by Nathan. And it will be about Python usage within LHCb experiment. So yeah, welcome, Nathan.
Okay, thanks.
Still muted.
Thanks for having
me. Oh,
yeah. Thank you. Yeah, so as Oksana said, so the goal today is to share some feedback from the LHCb collaboration and share how different analyzers are making use of all of the great Python tools that are available in the ecosystem. So to first start, I want to highlight a bit the data workflow within the LHCb collaboration. So here from our trigger and offline processing, we have a bunch of different steps, and this relates to quite a large infrastructure for the data processing, where it is primarily built on C++ backend. However, it makes use of a lot of Python steering for option files, for different calling of the different C++ classes, all of these sort of things, running the algorithms, defining the algorithm order, all of these sort of things are steered with Python and is made a lot more readable and user-friendly to have this Python steering. And additionally, there are still many tools available with the ability to complement the structure. Things like doing checks, doing tests, all of these sort of things on the different steps to make sure the process is working the way that we expect it to. So the tools, though, in today's discussion are going to focus primarily on the last two stages, which is our analysis productions, and then finally, afterwards, the user analysis, where people are actually doing their physics. And so again, the goal today will be a little bit different from some of the great talks that we've already seen at PyHEP, is to share the Python tools and the experience of the analyzers from the LHC collaboration, not so much a hands-on experience, but what people are doing, how they're using it, and what areas that have some holes or what areas are working great. And we want to share our feedback to the Python community. Okay. So moving on then to slide 3, we have our analysis in the LHCb. So for our data format, the LHCb analyses primarily use flat n-tuples, so your standard root files outside of the physics application stack. Additionally, there is a filtering of these samples to create the n-tuples, and this is done with individual grid jobs in the past. And now moving towards the LHC run 3, this is looking to be centralized. Additionally, people are making use of SnakeMake. And so this is utilized to create reproducible and scalable analyses. And if you're not familiar with SnakeMake, it is a build system entirely based in Python, which allows analyzers to basically rerun their analyses and make sure things are happening in the same order that you would expect it, and allows for cross-checks between different users. Additionally, in the same sense, people are also making use of GitLab CI to do a very sort of similar thing. So not just unit tests and things that you normally would associate with a continuous integration of your Git system, but allowing some reprocessing and reproducibility of analyses by running it through with the GitLab CI tools. However, there are some concerns with the data access and caching of the different stages with this. And for people familiar with LHC experiments, there's a lot of data to deal with. So this can become troublesome, and people are working on ways to get past this. Additionally, now the collaboration makes use of software environments, and they make the use of these environments to run the analyses so that people are trying to work in the same nutshell. In the past, on interactive clusters, there was the abuse of physics application environments and using central CERN building blocks like from LCG. But then locally, you had users that had much more ad hoc builds, some homebrew things where they've made their own tweaks, and then maybe some system package managers where you can get to a specific version or these sort of things. But across the board, there was a lot of room for differences. So now moving towards run 3 and beyond, on our clusters, we want to employ version conda environments installed on CVMFS. And these then will be centrally managed so that people are getting access to the same software stack. And then locally, we can make use of Conda or Mamba with Conda Forge so that people can check out the same software and make sure that when they're using these different packages available, that they're using the same thing as the other ones that they're working on the analysis with. Okay, so now I want to move to the analysis productions within LHCb. So what analysis productions are is a centralized sample filtering to create manageable n-tuples for the analyzers to use, to go from your 2 terabytes of data that you initially have after the trigger and maybe some skimming, to now down to something that's smaller and able to be used, maybe order of 50 gigabytes, where people can have these locally and make use of it. And so for this process, some of the tools that are used is Uproot. And so as probably been discussed over and over through the Python community, Uproot is an input-output for root files, and it shows better performance than root zone file IO methods, and allows, additionally, what's great about this is it allows to read the data straight into arrays, data frames, these sort of things that people can then make use of the other nice Python tools available. And then following up on that, we have awkward, NumPy, and pandas, which are used and allows for the physics tool manipulation handling before shipping the output to the end tuples. And this is flexible use with uproot, and it has the additional nice flexibility for developers where you can change between the different formats during development. So if one person wants to use NumPy, somebody else wants to use pandas, you can make use of using these different things all while staying with the uproot package and then shipping off things to the output and tuples in the end. Some feedback given from the analysis production groups. So they've seen a significant improvement in the reading of files with the Pythonic tools. And this then leads to a very huge performance boost when you're handling many files like they are at the production level. Additionally, Pythonic data frame structures integrate more nicely into other libraries rather than using Root's custom version, where often the Python libraries talk and communicate with each other better than trying to use a root library that's been developed mainly with C++ in mind, and then trying to adapt this to Python and the other available Python libraries. So having something that is more compact and working together with each other is great. However, there is still some missing functionalities. For example, JSON serialization for the HIS package. But some of these things can be manually implemented reasonably. And because it's Python and people are very handy in developing here, filling in some of these holes isn't too bad. And then here now at the final point, and you'll notice a running theme through the talk, lack of documentation in some libraries makes things difficult. And what then happens is you need to have expert understanding to trawl the source code to make sure that you can figure out what's going on and then how you can put things together. And oftentimes when you have many users in a large collaboration, this can be difficult for younger students as they're trying to get into things and make use of these packages. So I'll probably say this on almost every single slide throughout this talk, but improvement and availability of documentation is the way to go. Okay, now I want to diverge farther down the line, moving towards our analyses. And first I want to highlight an LACB publication, so a prompt charge particle production paper, which was done solely using the PyHEP tools. So basically everything after the data processing was all performed with the Python HEP tools available. They made use of uproot for interfacing with the input root files. They made use of boost histogram to fill the role of your classic root histogram classes. And the bonus here was the functionality and user-friendly availability of the multi-dimensional histograms within boost histogram. Now, one might be thinking, okay, we say multi-dimensional histograms, but what do you actually mean here? Because I just show 2D plots. But what you're actually able to do then is additionally, you'll see that you have a differential distribution within ADA. So you have a binning of the ADA distribution going from 2 to 4.8, and you can have 6 different bins there. And then additionally, you can have some maybe binning on your PDG ID to get the different channels or these sort of things. So now you're up to a 4-dimensional histogram where you can store all of the information that you want to plot down the line in the future. And you can carry it along in one Python object, which is really handy. It compacts things and is really, really nice to use. Okay, and then moving on now to the fitting side, makes use of iMinWe, which is a user-friendly interface to MinWe2 to process the minimization. And then the PDF for the analysis was built in Python using the various SciPy library components to put this thing together. Now, some feedback from the analysis group. So what's great is the standard scientific Python stack can handle a good portion of the analysis flow. However, there are still some cases for people to try and find a splash from other HEP tools when all of the things aren't quite readily available, or if the exposure to some tools is missing. Additionally, then Python tools often are more lightweight, like uproot and flexible, such as boost histogram, than their root counterparts, which even though we might not have the exact same performance, is nice for people to get started right away and work even on their own personal machines. Additionally, Python packages often have a simpler implementation and a lower learning curve, which is great for getting students involved. And we know that students within these large collaborations is really the backbone and continues to drive the field. And so a recent survey found that about 50% of LHCb analyzers were using Python-based analysis code, which is great. And I'm sure this will continue to trend upwards. Additionally, many users often try to find alternatives for fitting procedures, but often tend to fall back to RootFit when other fitting tools aren't mature enough for non-trivial fits. So we need to consider that in development. Additionally, bootstrapping availability in the past was missing up until recently. However, now the resampling package has been added to PyHEP, which has filled this hole. And additionally, now the architecture can still benefit a bit from a general purpose error propagation library and the Jacobi library, which will be discussed in this workshop, is been developed and hopefully will address this gap. Okay. All right, now I move on to the amplitude analyses and their tools in LHCb. So the amplitude analyses are the most computationally heavy analyses in the LHCb physics program. There's many tools available to try and fill this niche. However, today we're just going to focus on one, but I do want to say that there are many more on the market. There's tons of them out there, but today we'll focus on TensorFlow, which is an open source computing software which has been provided by Google, and it serves as a low-level library to provide the building blocks of the complex fitting procedure needed for amplitude analyses. Additionally, a number of institutes are making use of the GPU availabilities for fitting, DNNs, and amplitude analyses and these sort of things. And there is an additional potential to exploit the large LHCb HLT1 GPU farm outside of data taking to do these sort of things like very complex fits or DNNs or these large amplitude analyses. An additional Python package then making use of this is the AmpliTF, which is a library of simple HEP applicable functions using the TF building blocks. And it gives a nice simplified class structure, which allows for accessibility to developers and application to other libraries, which is great. Okay. So the primary goal then that these analyzers want to share is that when a framework isn't always readily available, there needs to be an efficient computation with the trade-off between time to implement the code. And this is very, very important. And the processing time it saves when running. So just because the code is great and it processes things really, really fast, if it's a huge nightmare to get it set up and running, as analyzers, this now becomes a net loss over time. So additionally, there's frameworks like ZFit, which will be discussed at this workshop as well. They do it. Makes use of IMinWe for the minimization backend, TensorFlow backbone hidden from the users, and is quite flexible. So additionally, TensorFlow is heavy and not always hardware accessible. And so the community continues to look beyond TensorFlow. Things like JAX, PyTorch, etc. Are coming into the fold, and people are trying to make use of it. And this leads to the last point on the page. When developing code and frameworks using TensorFlow, developers need to try to keep it as a building block and not a cornerstone. What this then allows is to easily migrate to another computation engine in the future. So if you want to switch from TensorFlow to JAX to PyTorch, your code should be malleable enough where you can basically remove one block and put in a different block, and then allow things to proceed ahead. And this will allow, as newer, more powerful computational engines get developed into the future, you can take these and plug them right into your package. All right, and now I want to highlight just very briefly ZFit. There will be a larger presentation by Jonas, I think, later in the week. So ZFit is a general purpose fitter, and it tries to harmonize workflows and include some advanced functionality beyond what is provided by the standard Python tools. So as stated before, it makes use of TensorFlow as a backend for parallelization and GPU support. But additionally, it makes use of uproot, boost histogram, and IMINWE, which we've discussed earlier. And finally, it makes use of the HEP stats package, which is used in conjunction with ZFIT for further statistical inferences. So currently, there are roughly about 100 users across LHCb and the Bell2 experiments making use of this package. And it has it serves two primary analyses use cases. The first one being simple 1D mass fits. So the Pythonic package allows for easy implementation, very readable for newer and younger students that are just starting to get involved. And you can plug and play and get these things going for your simple 1D mass fits. And then on the complete opposite end of the spectrum, the next use is for extremely complicated fits. Because the package is extremely malleable, it makes for many fits possible, such as the matrix element for the B plus, the J psi phi K plus analysis, which is down here in the bottom. And you can see all of the complexity and different moving parts within this analysis that need to be fit together. And having such a malleable framework allows for these sort of things to be functioned. So some more feedback from the ZFIT team. So the primary goal then, similar to what was coming out of the amplitude analysis people, is to have an accessible Pythonic fitting framework, which is beneficial both for new and experienced users. And they want this to be integrated well within the general Python data science ecosystem in general, and in more particular, the scikit-HEP packages. So the team continues to further pursue integration for plotting routines and different statistical treatments, some with HEP stats, some standalone. However, at the time, there are still some PDFs which aren't supported. And when these aren't supported, that leads and opens up a potential for users to fall back to RootFit rather than trying to develop the PDF using TensorFlow. So the package would benefit greatly from additional support and feedback from stats experts. So fitting is a huge topic with many different avenues. There needs to be support from experts and the implementation of statistic or specific statistic recipes, either in the development or in the feedback form, to make sure that the statistical implementation is being done correctly. Okay, moving on now, I want to highlight the PID Calib2, which is a package that is made use within the collaboration for particle identification and calibration. So this is a rootless particle ID efficiency estimation. And so here there's some software tools that are needed to extract PID calibration between data in Monte Carlo. And this primarily comes from the fact that PID is very tricky to model in LHCb, particularly because of the simulation of the rich. So having a data-driven correction of the simulated events using real signals is a great bonus. And to do this, they make use of a lot of Python packages. To start, running theme, uproot and boost histogram, simple access to root files with Python and subsequent histogramming, and additionally makes use of this higher dimensional binning, which was mentioned earlier. Additionally, then for plotting routines, we have matplotlib and a PyHEP. So this is a simple plotting, easy installation, very lightweight, and it additionally is great for LHCb people, where MPLHEP, you can apply your specific LHCb style file, but you also have the same thing for CMS and Atlas and these things available. And then finally, it makes use of the xrootd package for accessing remote root files with a Pythonic interface. Now, the framework or the data class used here is pandas, and it's used for manipulating tabular root data to vectorize the efficiency calibration. So there's a significant improvement over previous C++ iteration, primarily from the installation and overhead. And you can see here, again, making use of the nice matplotlib plots and the higher order histogramming. Sorry. Okay, so feedback again from the PID Calib2 group. So the Python packages are simple to install and lightweight. This is great. This is great to ship to analyzers to use in the end product because they can install things and get things going right away. Additionally, using large data formats for centralized calibrations can become costly. So they want to continue to look for ways to cache between users to lower overhead and make use of some of these Python tools along the way. Additionally, as been mentioned, an event-by-event calculation is cumbersome, and there's a huge benefit to vectorization. So as developers within the Python community, and as you're putting together your package, there needs to try and be support for new users by sharing examples of how you can implement vectorization into their code, rather than using your standard event loop where you go over each individual event, where while it's simple and it's easy to understand, it isn't the best practice. So by having these examples of vectorization is great, and it helps new developers get involved and do things the right way. And then finally, of course, documentation is very good for some Python HEP packages and very poor for others. So even though there may be benefits of using these packages, the installation and implementation headaches don't outweigh these benefits, leading to a net loss and pushing people back towards some C++ methods. Okay, and now finally, I just want to highlight some of the additional tools utilized within LHCb, and I believe all three of these have or will be talked about within this workshop. The first one being Particle. Particle is a simple Pythonic interface for PDG information, and it's extremely handy for analyzers with many decays to consider in a single analysis. For example, within WinLHCb, some analyzers utilize over 100 individual PDG objects in a single analysis. So having a Pythonic interface to access the PDG information easily is great, rather than reading through the pages and trying to find all this info. Additionally, PyHEP has started to be used. So a new rare decay search is benefiting from the simple implementation to an ecosystem that normally doesn't use a lot of native his factory or his fitter or these sort of things. But by having this PyHEP as the Python interface to the HisFitter template builder, being independent of its root implementation is great. Additionally, and then finally, decay language. So a package for visualizing and manipulating decay chains with the Python tool. And it often is taking the .dec files. And for example, these are the basis of the LHCb Monte Carlo generation. So for analyzers within the collaboration, these are used a lot. And it can take these as input. Users can produce then simple but informative infographics like the one here below, describing their particle decays. For example, you have a D star and you can see its different decay modes. And then even further down the line, the second order decays of the D plus pi 0. Okay, and now to sum up everything, I want to give some feedback from LHCb as both developers and users. First, we want to share we are developers. LHCb members play a big part in driving the developments of the HEP software ecosystem on many fronts and not just users. And I can shout out some of the packages that have been discussed in this workshop: Particle, Decay Language, CFIT, I'm in We2, developed by people like Eduardo, Jonas, Hans, Michael, etc. All of these people are trying to lead the way in helping in this development. Additionally, developing the tools in-house allows them to be directly applied to analyses and other LHCb specific software tasks. However, there's still lots of room for more hands to get involved to try and generalize these things to the broader HEP ecosystem. Additionally, standard tools, your standard Python science package, tend to draw more interest, especially because of the application to life beyond academia. Many of our students are getting involved in HEP, but eyes forward to the future may not want to stay in academia and are looking for a step into the industrial field. So having access and training and experience with these standard tools is more appealing to them. Additionally, students are often learning Python tools in their university classes now. So the attraction to Python tools continues to grow and is great to see. And then finally, as feedback as developers, we want to encourage that people continue to strive for outreach and education, like is being done here, to try and get your packages into the hands of new users. You can have the best package out there. It can work great and perform at the highest level, but if people don't know about it, or people can't get it implemented into their code, okay, you've lost the interest of users. So you need to make sure that you carry on to the final step. And then additionally, now as users, our feedback is that it's very important that tools have relevant documentation, and there's huge advantage to accessibility if working examples exist as well. such as things like these Jupyter notebooks and things that people have been sharing this week. Additionally, availability of some testing tools is great, and the flexibility. So we know physics analyses and HEP analyses have lots of specific use cases. So having a test bed which shares a more wider scope is very valuable, rather than focusing on one specific type of example. And this is especially important for younger collaborators. Additionally, we do want to give feedback to the developers in the Python HEP community, because bug fixes when implemented are always done not always done, but often done quickly. And this is really encouraging and great for users. And then installation is quick and simple. This is a huge bonus over root software, which often takes a bit more to get things installed and get things running. By having this Python packages and being able to run them locally on your machine with a simple setup, just downloading Python 3 and pip installing whatever you want is wonderful. And then finally, new users can often be overwhelmed with the choice and struggle to know which tools to use. There's so many out there. So increased training, like at this workshop, and improved documentation can help these users to make informed choices on what they can apply to their analyses. So yeah, as a final conclusion, I just want to say there's a lot of advantage to using the scikit-HEP and Python HEP tools. Please keep them coming. Thank you.
Thank you so much, Nate. So we have actually quite a lot of questions in Slido. So I would propose if you could take a couple of them, and then we, as usual, move discussion to Slack.
Okay.
Do you have a Slido link, or I will?
Yes, yeah, I have the link, but I'm not sure quite how the threading in Slido works. But
so
yeah,
Jim tried to help you.
Yeah, okay. So let's see. The first one here we have, you mean pandas data frames are preferred to our data frame. Despite the name, pandas data frames are very different things from our data frame. Both to use. Okay, so I think Jim gave a good answer there. Yeah, so maybe I'll skip down to the ones that
yes, let's go there, and then we move to discussion.
And then, yeah, thanks. So you mentioned that additional computational backends beyond TensorFlow are considered. Which ones exist as usable alternative backends now? I believe JAX and PyTorch have been utilized within the collaboration. I don't know to what full extent, but these were the two that have been mentioned and were given as feedback. The next one, with GitLab CI, you mean unit tests or actually running the analysis? Even with tests, you might need access to data or Monte Carlo, so the data storage is problem. Yeah, so it's both of these things, right? So first of all, you can do unit tests. Generally, these are, you can make use of much smaller data files for unit tests, and these become simpler. But people now want to have this full analysis reproducibility within the GitLab CI. And so within there, with the LHC experiments, you know, the data files are huge. So there needs to be different ways to cache these things along the way, because you have many different steps and the data has many different iterations along the line as you manipulate it and do different things and get to your results. So it's both of these things. So in the current state, being able to run unit tests, I don't think is limited a bit by the data, because you can use a small file, but mainly stretching out to the full analysis. Okay, how is X-root-D used to read remote root files? How does it deserialize content of the file into memory for processing? Unfortunately, I don't think I have the specific answer for that. I can find it for you and get it back to you, but yeah, off the top of my head, I don't have this information on the package. And then finally, is installation of these Python packages easier than root? Smaller, yes, but root is just a controversial installation distance. Right, so root in itself has become a lot easier to install over than from when I got started in HEP 6 years ago or so. But yeah, it continues to try and get caught up. But then as root is its own package, there are then many different things that are built on it. And then oftentimes you need things like CMake, this build procedure, all of these different steps, whereas the Python packages, you can install them locally to your machine, you get them right away. You then just import them directly at the top of your Python script. And this sort of feature comes back is quite simple, and especially for younger users who want to know actually or exactly what they're doing. Having this Python readability is a huge benefit where, okay, I know I'm using this package because I told Python I want to be using this package, and now I'm using this information, whereas root is this gigantic thing. You have to then worry about oftentimes if you want to use the compilation or these sort of things. So yeah, I mean, you can of course use root in Python itself, but then you have to try and find the different root classes, which can be quite cumbersome, whereas some of these different things with Python is nice to be able to pick out directly.
Nate, thank you so much. It was really nice motivation talk, and I hope everybody who has like follow-up questions, just go to Slack and let's keep on discussing there. Meanwhile, sir, we're like 10 minutes late, but let's move to a talk by Luca Canali about how we're going to use Spark, Apache Spark for analysis. And look at you. I'm able to share the screen. I see you.
Okay, right. I should be sharing.
Yep, I see your slides.
Can you see it? Okay.
Thanks.
All right. Okay, thanks, Oksana. So I will start. Well, thank you all for tuning into this talk. I'm quite happy to present about some basic physics analysis implemented using Apache Spark. So I'm Luca Canali, and I'm in the CERN IT Spark and Analytics Services, and also with the Atlas Data Engineering and DBA team. Okay, I'll move to the next slide. All right, sharing doesn't move, so okay, let me reshare. Right. Okay, what's happening? Okay, so a bit of motivations about this work. So the contest is the Spark service at CERN, and then I was getting questions from the Spark community saying why doesn't have use Spark, or what are the blockers, and also people in the high energy physics are interested also in looking at Spark and other tools to parallelize their Python analysis. So I went to do some small notebooks I will show today, and also wrote a blog post on what works and what doesn't. So we'll cover quickly today, so we just skim through it. So it will be a few slides to introduce some of the key points about Spark, and also I will mention what works and what doesn't work. Okay. Things that don't work very well, the sharing about some. Okay. Just do something. Sorry about that. So one of the key selling points about Spark is the adoption in the industry. So this is a tool that is very much used. So you're probably interested also because most of you have heard about Spark, even if you have not used it. So who is using it? So Databricks is a company founded by the people who started Spark and are still the top contributors, and it's a key part of their business to sell and optimize Spark platform, but they also contribute to open source. Also, all cloud vendors offer some big data tools, and they include Spark. And many of the tech giants actually internally they use Spark. So this emerges from mailing list, and also contributions that they do to the Apache Spark project. For example, they hire Apache Spark PMCs. And so this is very, very active and financed by senior software engineers at these companies. At CERN, we're using Spark mostly in the Hadoop platform. There are various use cases, IT monitoring, IT securities. Then we have a project with the experiments computing data. For example, I've been involved with the Russia project, and they do some reporting by using Spark. And then for physics has been used by different projects. You'll be familiar with our data frame, and then there's also project CMS Spark, CMS Muon POG, and there are various others. We also provide Spark on Kubernetes clusters, and people can access Spark via notebooks using the Swan service. Various communities use different languages. Python, of course, is very popular. Other people use Scala or Java. And then in the Accelerate community, there is a very large project on the petabyte scale that is using both Hadoop and Spark is the main API. So actually, they have based an API based on Spark, where the users can analyze this very important data from the accelerator complex. Okay, let's first start with a demo to answer the question. So can Spark do some physics analysis? Let's see. So I have all the code is in a GitHub repo. The link is on the slides, and you can see it also here. And there are different type of notebooks that are built, and they are detailed in the README. So the data is also available. It comes from the open data. I typically transform it from root to Parquet. We'll come back to that, but we could also read directly root files from Spark. So I'll start with this very simple demo of the Muon mass spectrum taken from a nice demo from the root team. So I just basically translated it using Spark APIs. You might be familiar about this. So the first thing to do is to download the data. I've already done this, and it takes about a minute. And then there is a special package, we'll come to that, to do histograms. I already installed it. And the next thing is to actually install Spark. You can simply pip install PySpark, or you can download it. Since I use various versions, I typically download them and then specify the version that I want to use. Otherwise, with pip install, you just get the latest. Okay. All right, let's create the Spark session. Here I'm just using a local PC for this demo. I could be using Swan or other services. There is a version of this demo that runs on Colab, for example, if you want to run it there without having any additional computing resources. So what I've done, I have created a Spark session. This initializes Spark and the various memory areas. Then I went to read the Parquet file, or at least I defined a data frame that would read from a Parquet file. This is the file that I downloaded in the previous step. And then I just run a simple operation. First, give me the schema of this data, and then how many events are there. So the schema is a nano-EOD type of schema, quite simple and flat. So we have how many muons are in a certain event, and then muon PT, eta, phi, and charge, mass and charge. And there are about 6 million events in this file. First thing, we want to do a filter. So we want to have only 2 muons of opposite charge. And as you can see, this can be expressed in a Spark data frame API in a quite intuitive way. And then we computed the muon mass using this simplified formula. This is a SQL-ish way of doing it. There are, of course, other ways of applying functions that look more like, for example, pandas and data frame. But as you can see, it's quite clear what the computation does. And then histogram computation, since we want the output of this will be a histogram. This is done using a Spark data frame API, but it's a bit of a boilerplate. It's actually at the end of the data frame. So what I've done, I put together the 3-4 steps that are needed into a small package and pushed it to PyPy. So I just have to specify minimum, maximum value, a number of bins. These are very simple frequency histograms, 1D histograms. Okay, so I define a new data frame. It is a transformation of the previous data frame with filter and mask calculation. And actually, everything is very fast so far because we've only done data frame operations that are lazily executed. Now we tell Spark to actually give us the data. So, and we are putting it into Pandas data frame locally to this machine. And so the computation is triggered. The computation could be many steps. In our case, it's about 3 steps. It could be many more, and Spark puts everything together and optimizes it. So this runs in about 12 seconds. So now data is local in a Pandas data frame, so we can have a look at it. You can use a little bit of a matplotlib syntax to get the nice plot of the various particles and resonances that this data set contains. Okay, and we can also, we finish, we can stop Spark. And this is the boilerplate code that does the histograms, but it's a little bit outside the scope of this talk. Okay, so I think we answered the question, can Spark run some basic physics analysis? And let's see what else we can do. Okay, so the main abstractions that we use are data frame. Data frame should be quite familiar to you from other environments if you haven't seen Spark yet. It's basically a table-like abstraction, very similar to Pandas data frames. Very important is that data must have a schema, and this is a very good thing about energy physics data. This typically has a schema. And then internally, Spark will parallelize the data, and will also the data frames will be immutable, which allow parallel execution tolerance and fault tolerance at scale. We come back to the point of performing at scale, which is obviously very important. Okay. Another thing that we have seen in the notebooks are how the data frame operations can be done. These are simple operations. A filter is just dot filter, and I will specify the filter, and then expressions and formulas, also complex one with square roots. Also here we are using arrays. As you can see, we index them. It can be done and expressed easily with the Spark API. And histograms, I already commented about this package that collects the various steps that need to be done. So I chose to generate histograms with the Spark data frame API. So when we run this at scale, Spark will be able to parallelize it. There are also other solutions like histogrammer, for example. So how does Spark run jobs at scale? So there will be a driver with the Spark session and the user code, which is communicating to a cluster manager, which could be a Yarn cluster manager or Kubernetes or a standalone cluster, where executors will be spawned, and then Spark will run there in parallel. Typically, data will be parallelized. Chunks of data, so partitions, will be executed, will be computed on by the different executors, and then the results will come back to the driver. Another important point about Spark is the ecosystem that Spark has. And so we have seen there is a core engine. Here we are talking mostly about the data frame API with a little bit of Spark SQL, which is almost the same for Spark. There are also other APIs. Spark can talk different languages, SQL, Python, and then Scala, Java, and R. A very important point is that Spark can ingest different data formats. It can ingest root, or Parquet, or CSV, for example, both in reading and writing. It can be interfaced with many storage systems like Hadoop, EOS, S3, and then other like RDBMS and streaming data, which are outside the scope of this. And then where to run Spark. So basically here I've been running it, the demo #1 on a desktop machine, but then Spark can run at scale on Hadoop, on Kubernetes, or on a standalone cluster, which can be created. For example, if you want to use PyHEP resources, one can create it there. At CERN, we have in production various clusters. It's mostly Hadoop, but also cloud containers that run Spark. In total, about 5,000 cores and several tens of petabytes of storage. And then one can also use Spark on Cloud containers on EOS and S3. Another interesting point that I quickly mentioned earlier, and I want to further drill down on, is that you can run Spark on our Swan service. These are basically Jupyter notebooks that you can access via web interface. Probably several of you have already tried them. Otherwise, this is the link. And Swan is integrated with the Spark cluster at CERN, so that's one can use that, both the Hadoop clusters and the cloud containers clusters. And it's possible to access HDFS, of course, but EOS and S3 as well. Okay, now just since we are talking about Spark at scale, I wanted to show you a quick way on the same demo that I've shown before can also be run at scale. So we will not be running it at scale, but I just show you because it's basically the same. It's exactly the same thing that we have seen. But instead of allocating a Spark session locally, I can allocate it on a Yarn cluster, for example, or on a Kubernetes cluster. The syntax would be different for Kubernetes. There are additional parameters about the number of executors and the memory that I want to run. The rest of the code stays the same. And in this example that you find in the GitHub, so I'm reading data which is available on the Analytics Hadoop cluster. This is a larger version of the data. Actually, it's 100 times bigger. This is 6.5 billion events. And in this demo that I ran, so you get the same graph because the data is just simply copied for demo purposes, and in about 30 seconds, and it executes this, going in parallel on 20 executors with 10 cores each. Okay. Then another important point for high energy physics is to handle complex schemas, because this is what is there typically for data. So we've seen in the demo, actually the demo was a little bit flatter schema, but one can have really deeply nested schemas. The more nested, the more you pay in performance, but Spark can definitely handle it. And then there are various ways to manipulate arrays, so data that is nested. So there are various array functions in Spark, and then also explode function that transforms array data into rows, and then one can use table functions. There are also some higher order functions where one can inject, map, and filter and aggregate operations on the array elements. And finally, the final solutions, if nothing else works, is our user-defined functions. One can write them in Python or in Scala, but then one can write the UDF in Scala and access it from Python, for example. One can also mix the languages. So I will go now to demo number 3, where I took some of the task in the HEP analysis benchmark. The link is here, and it's a very nice benchmark that gives some target to this evaluation. And so I did some of the tasks there. Okay, a benchmark. This one, similarly to the previous one, has also a Colab version that you can run in Colab. Since the data amounts are quite small, it runs there as well. There again, one needs to install Spark if you don't have it yet, and Spark histogram, get the data. So you download the data. Sorry, so first thing is to get the Spark session. And we are back to using local Spark histogram with the boilerplate code. for these simple 1D histograms using the data frame API. Okay, here in this data set that comes from the PyHEP benchmark, we have many more fields, quite a lot of them, and about 6 million events. Yeah, single mute samples. That's the name of the file. The first benchmark task is a very simple one. Basically, it's just an histogram of the missing transverse energy of the events. So we just feed it to the histogram creation, transform it into pandas and matplotlib on the pandas in the local machine. Task Q2, it's also quite simple. Here you can see these are the jet PT, the transverse momentum of the jets. So you can see there are arrays of different sizes. For example, these are the first 5 rows. And then for this one, I chose the solution of just putting everything flat into a table, given how easy this task is, and then just create an histogram out of that. And then you get a distribution. Then this is plotting on transverse momentum of jets with eta, the absolute value of eta less than 1. So I think these tasks also make it quite interesting as a tutorial for somebody, for example, who is not in PyHEP and wants to see a little bit what are some of the basic blocks of a PyHEP analysis can be. Let's say some data scientist or the data engineer who is more familiar with Spark than anything else can have a look at this. They have an increasing complexity and show some of the operations. And finally, we typically end up with a histogram, and then the complexity is going up. Let's see how we're doing with time. Okay, maybe we just do this one. The transverse momentum of events, there are at least 2 jets. So here we have more constraints. So we want to have the missing energy PT and then the jet PT. So we just take those. And here we start having some functions that do cardinality, and then they push a filter inside an array. These are some of these high order functions that I mentioned. It becomes a little bit fancy, but still feasible with Spark functions. Then when it gets more complicated in further tasks, but we will not get there, we do need UDLs to operate on that. Okay, I think you get a gist of it. It's probably hard to do much more. I wanted to show you just another set of things that I've done. I took the Atlas X open data demo again, and there are different complexity here. For example, in one of these notebooks, I recreate the figure 2 of the X paper, but I will just go for the simplest one. This just takes it has quite a small amount of data from the open data. Yeah, so here we still have the previous Spark, so that's right. We are running 2 Spark sessions on this machine now. So as you see, a very small number of events for this. But then one can have filters like events with 4 leptons, and then selecting 2 pairs of isolated leptons, which comprise of 2 leptons the same flavor, so becoming a little bit interesting. And then the flavor of the leptons needs to be filtered. These are things that can be expressed quite well with the data frame API. And also, Spark doesn't have a concept of 4 vectors, so I'm afraid these calculations need to be explicitly made. Okay, I can implement all the formulas that are needed, and then there again, this goes into a histogram, and we get, for example, we see the Z boson and the X boson mass. Okay, this just gives you a flavor of what is possible, the very basic analysis, or at least let's say, components of analysis. Now we want to wrap up. So the good parts. So the Spark data frame API is a powerful abstraction and a rich language. It allows to do data preparation and analysis. It's mature and as an industry reference, and can handle complex schemas, which is a must for high energy physics. So one can run data frame locally or at scale. So for performance, one can take advantages of clusters, Kubernetes, so for cloud or Hadoop. So probably cloud resources and standalone clusters, let's say on HPC, is what can be of most interest for this community. And then there are integrations with a large ecosystem. Many file formats can be ingested, including root. Many storage systems can be used, including OS, HDFS, S3. And then let's see the things that are a little bit missing. So where Spark still has to climb up a steep incline to get up to par with other analysis tools. The performance. So there are several areas where the improvements are needed. Python UDF, we haven't seen them in the examples, but okay, I can mention that they work. It's possible to write Python UDF, but they typically don't perform too well. And Scala UDFs, so UDFs written in Scala, typically perform better. As I mentioned, it's also possible to mix the languages, write the UDF in Scala and call it from Python. And then there are Spark functions. There are also some performance improvements could be done. So these higher order functions, we have seen briefly one, need a little bit of boost in performance, even though they already work reasonably well. And there is no knowledge of Lorentz vector at the moment. This is something that maybe can be added to Spark. And in terms of the Spark engine, so it runs in the JVM, which is compiled, it's written in Scala and Java, and has to compete in such, so to speak, with C++ code that is used currently in the mainstream analysis tools. And this is, of course, it's not the same speed. People in the Apache Spark community are already working on vectorized execution and putting some parts of the Spark engine into C++. So maybe this can improve. In terms of data format, root is the king in this domain. It can be ingested into Spark thanks to the Lorem library, typically maintained by Andrew Melo. But there are limited resources for that, while Apache Spark or also Apache ORC format works much better with Spark because a lot of optimizations and many people are putting a lot of efforts into that. So that if data is in Spark, is in Parquet format, it's much better for Spark analysis. And then flatter data is much better for Spark. So in this respect, nano AODs work so much better than the previously deeply nested formats. And in the future, I see so Spark is achieving a lot of improvements. I already mentioned people working on C++ extensions. Also, the HEP community is doing amazing work in developing Python frameworks, and these things together can also help the development of analysis with Spark. At the moment, as you've seen, it's just for basic things. Maybe in the future can do more performance and more functionality. So I'll be very interested to hear if somebody is interested in trying out Spark. You can reach me, and I'll be happy to answer your questions. Also, I would like to thank many people who helped doing this work and consulting, and many are in this community. Okay, thank you very much for your attention.
Thanks, Luca. So I think, yeah, let's check Slido if there is anything there. Yeah, there is a question for me. How many resources are allocated for Spark specific computation at CERN, just, to promote more to community what is available? And
Yep. So for example, I can show you. So Swan is integrated with CERN clusters. So with the Hadoop clusters and the cloud containers, and these are the resources available, for example, in the Hadoop. At the moment, the main Hadoop cluster has 1,800 cores, 13 petabytes of storage, and this is shared, of course, and 13 terabytes of memory. So what happens when a job runs on Spark from Swan or from other clients into Hadoop is that there is dynamic allocation of resources with the maximum. So typically you get a few hundred cores, but several users can come into the cluster simultaneously. And then there are also cloud containers where there are about 200 cores. And then of course one can bring in resources from the cloud, and that will be, for example, an experiment can bring specific resources and run Spark on that. But these are the ones that are offered, let's say, from IT to generic communities.
Thanks. I don't know if you see slide the link, or I will just read for your questions.
So what is AOD? What's it? Is a data format, I guess.
Yeah,
but yeah,
CMS
somebody else can give even a more detailed explanation about that. We mentioned a lot of LHC experiments. Normal seems huge. Do you think Spark is being used outside LHC experiments? Yeah, Spark is being used, for example, CERN is used. One of the main user is the accelerator logging infrastructure. So I share the same. It's used by many, and this is one actually, even a better slide. Sorry. But yeah, already in physics, there are other people using it besides the analysis, and for analysis is only experimental. So so in production, so IT monitoring, so one of the pipelines goes into Hadoop, and then so data is sunk there, and it can be used for long-term processing. IT security also has jobs running there for the detection of attacks into the networks, and then the experiments computing data, for example, the Rusho project. So this is use Atlas and also CMS as a file catalog, and needs to do large reports. So exports the data from the relational database into Hadoop, and then runs Spark jobs. And also the export is done using Spark. And then of course our data frame makes a use of Spark that is different than what I've shown here, but also it's using through the same platforms. And then there is a project called CMS Spark, and I think last year CMS new POG was presented at PyHEP 2021. And then various people have different projects, smaller projects, but they run it. And there is this very large project where an API based on top of Spark is runs on this NSCAS platform. This is an accelerator logging complex where they log basically the thousands of sensors from the various accelerators and subsystems. And then when people need to query that, they will, for example, connect to Swan, ask for the events that they need, and they will get a Spark data frame back. And then they do the processing in that.
Thanks. There is one more question. I would propose to move it to Slack because we're already 10 minutes late, and it's like also a nice way to continue discussion in case people has more questions. So thanks a lot, Luca. It was very nice. Now we're moving to the next talk with Benjamin about who will demonstrate a bit as how works Coffee Work Queue Executor for realistic analysis for cloud.
Great, thank you. Can you hear me okay?
Yes, we can hear you. We can see you. Still no slides?
Oh yeah, it says I can't.
Look at, you need to stop sharing probably.
Oh yeah, I think that's it.
And FYI, the anonymous question was moved to topic distributed analysis. That's for the last talk.
Wait, Luca, can you stop sharing? Oops. Wait, can I do this? Okay, thanks. Thank you. Ben, does it work for you? Yeah, I see your screen.
Okay. Great. Yeah, thank you. I'm Ben Tovar. I work at the University of Notre Dame. And today I wanted to talk about some of the ideas we have been researching about resource management with the Coffee framework, specifically with the Work Queue Executor. So I assume that most of you are familiar with coffee. If you are not, I think this is going to be a very boring talk. But if you don't, coffee is a prototype for pulling together many different tools for a HEPA analysis. And the idea is that you write processing and analysis functions, accumulating functions, and then those get executed somewhere. Where things get executed is the task of executor. So there is like the task executor and Spark. And in this talk, I'm going to focus on the work queue executor. The work queue is a library to create scalable manager worker style programs to scale into thousands of machines and clusters. The idea that to use work queue and coffee is to send whatever work you need to do to remote clusters, either by themselves or in some container environment. Two of the advantages that work queue has when used together with coffee is, as I said, the resource management. And the other is if you cannot pre-configure where the functions are going to run, work queue has some tools to do that. So you don't need to pre-configure where functions are going to run. The picture that you should have in mind is that you have coffee running on top of the work queue executor, and they talk to remote workers, which run either locally or in clusters or in grids or in the cloud. By talking to those workers, they send the processing, accumulating, and all the functions that you need to run, and then they send the results back. And that's the most basic architecture that we have. In terms of installation, if you're following this from Binder, you should be set already. The only ugly thing that happens is that in order to make the examples interesting, I wanted to show you how you can run different functions at the same time using a single worker. That seems to make my Binder unhappy just because of the limited resources that it has. One way to fix that or try to fix that is to let work queue know the limits of my binder. So in this case, we'll read the CPU limit and memory limit that binder is giving us. In general, you don't have to do this. The workers know how to do to automatically configure themselves. The only problem in binder is that the apparent resources are not the resources that you are actually allowed to use. So this is the code that you see here. You don't need to do this, for example, if you're using Google Colab or directly in the shell from a Conda environment. So with that, let's go to the demo. The three things that you almost always need to import is the runner from Coffee, the work queue executor, and then a factory that will create the workers for work queue. And then for the purposes of this demo, I'm going to use the pretty basic processor in the testing items that Coffee has. So that's this will be the part of the analysis that you will write, for example, to match whatever you want to do. And then I'm going to use, we need to define which data we're going to run. And in this case, I'm just going to use a single file to make things fast and easy. In the demo I have in Binder, this file comes from HTTP. I copy it locally just in case something goes wrong. Now, the most basic configuration that you need to do for Coffee and work queue together is that you have to, saying nothing else, you have to define which port work queue is going to listen to for workers to connect. Later, we are going to see how this port can be configured automatically. But for the most basic setup, you define a port, you tell work queue which port is going to run, and then you define the runner for Coffee using the executor that we define. And that's all you need. The other thing that we need is to define our workers. And for that, I'm going to use the work queue factory. The factory allows you to define workers and it creates workers as it it sees work from the runner in Coffee. In this case, we're going to run the workers locally. But say if you're in a batch system, you can change this to use Condor or SGE and so forth. And then the factory will create the workers in that batch system. The other thing we need to say to the factory is where our manager is running, in this case, locally at a certain port. I'm also setting a limit on the maximum number of workers that I want. And finally, the last thing that you need to define usually is the resources of your workers. Say if I'm running for Condor, the resources that I define here will go to the submit file. So the workers will be created with the resources, or will be scheduled in Condor with the resources that you define here. Since we are doing these things locally, work you just trust that you know what you're doing. And if you override any values here, it will think that the worker has those values. So in this case, I'm just defining that I want my workers to have one core in order to be able to execute one chunk at a time. So I define my factory. And finally, we use context to run our executor, our runner of Coffee inside the factory object. So I give it our input files, the tree we are going to process, and then the processor that we define the testing. And one thing that you will see in this example, or you will want to pay attention to, is how the largest scene worker, that is the only worker that we connect, all its resources are going to be given to the tasks. So the current allocation that you will see. So if I run that, we see a bunch of statistics. Eventually, a worker will connect, and we will see this largest worker, as you see here now, with one core and some memory and some disk. All these resources get assigned to a task, so current allocation. And the same happens for processing and accumulating, preprocessing, and processing functions. Now, one thing you will notice is that WorkQ automatically measured our tasks. So even though, for example, for processing tasks, we say we allocated one core and 16 gigabytes of memory, really WorkQ is telling us like we are way off in our memory, right? Like these particular functions use less than half a gigabyte. So that's interesting information. That tells us that maybe we can run more functions at the same time. And to show you that, I'm going to manually declare the resources that each task uses. So the first thing I add is to change the executor definition to say all of my tasks are going to use at most one core. And I'm going to cheat a little bit and say that my local workers actually have two cores. So with that, we will expect to have two functions running at the same time per worker. And you'll see, again, once the worker connects, that the largest worker says that it has two cores and 16 gigabytes of memory, but each task gets assigned one core because we said that our tasks use maximum one core. And then all the resources that we didn't specify get proportionally divided. So we had 16 gigabytes of the worker. So now each task that we didn't specify gets 8 gigabytes of memory and 5 gigabytes of disk. And this happens automatically. And what else I wanted to show you here? I think that's it. Yeah. Now, of course, this works, but it's a little annoying because you don't usually know a priori the resources that your tasks are going to use. So something that WorkQ has automatically is that if you don't say anything, WorkQ will adapt the resource allocation according to the measurements that it sees on the tasks. And this happens automatically. The only thing that it didn't happen in our example here is that I'm only using one data file. So we created very little tasks for WorkQ to gather data. So what I'm going to do is to run the same example. Now I don't specify any resources for my tasks, but I reduce the number of events per task. And this is just a trick to create more tasks. So WorkQ has data to make it computation. You will see that at the start, each task gets allocated the whole worker, that is 2 cores and all the memory. But as tasks come back, WorkQ realizes, oh, this is too much for this task. And then eventually it will be able to run 2 tasks at the same time. So if I run that, we wait for the worker to connect. We see that the worker connects with 2 cores. So far, WorkQ has seen the largest task uses 1 core. Originally assigns 2 cores for all of the tasks. So we are running only 1 task concurrently, but eventually it realizes that, oh, this is way too much. So automatically it reduces the allocation to the task to 1 core and to 8 gigabytes. And this is done proportionally according to the maximum values that we see. I think the minimum task number is 5 or 3 or 5, I don't remember. And that's why you see that, for example, for accumulation tasks, WorkQ didn't have enough information to make a more educated guess about the resource allocation. There are other resource management modes that you can use. One thing, for example, is that if you specify maximum resources for your tasks, the automatic resource allocation still works, but it takes the values that you declare here as the maximum any task can use. And if a task goes above those values, then something happened that I will explain later. The other thing you can change is that for processing tasks, we take the maximum resource value seen for our allocations. We have seen this works really well for all the coffee workflows that we have tried, but it might be that some tasks are just outliers. And in such cases, you may want to change the resource mode to max throughput. And in this case, the allocation is not based on the maximum, but in some optimization where some of the outliers get retried using full workers, but all the rest of the tasks use less of the maximum that we have seen. And finally, of course, something you can do is to say, don't do any computation, just use the resources that I tell you, in which case you will use the resources mode fixed. And it might be that you only want WorkQ to account for your resources, but not to measure them, in which case you can also turn the monitor off. One thing that often happens with especially when you're trying new coffee workflows, is that the tasks are way too big for the resources that you have. This might be a combination that your processor really uses more memory than you thought, or maybe the chunk size that you choose, that is the number of events per task that you have chosen, is way too big, and then the task won't work. If you specify resources like that, like a maximum task resource, for example, like 60 gigabytes of memory, and no connected worker has that much memory, then WorkQ will just wait. It will tell you, I can run this task, and it will wait for larger workers to connect. And the same thing happens if you don't specify anything, but during runtime, we realize that some task is using more resources than the available workers. It does the same, it just waits, and it tells you that I need a larger worker. So either terminate me or feed me another worker larger. And an example of how that can happen is, for example, I declare my worker with only 4 gigabytes of memory, but I say that my tasks use 8 gigabytes, then that's not going to work. If I run this in the notebook, this actually will block because how I set the factory here. So worker will just wait for a new worker, but then the cell never terminates. And the way to go around that is that you can feed a worker outside a notebook, and we will see that shortly. Now, there are 2 things that happen when a task is too big or too large for the allocations that you specified explicitly. For preprocessing and accumulation tasks, they just fail permanently because there is no way we can modify those tasks so that they run with the resources that were explicitly stated. However, what we can do for processing tasks is we can modify the chunk size dynamically, and that's what we do with the work queue executor. And I must tell you that from this point on, if you've been following in my binder, some of the examples may not fit in memory now, so it may cause your notebook to disconnect. And I tried really hard to find values that work in my binder, but then they were not very interesting. So if you want to follow this, you can either do it locally or in Google Colab. So one thing that WorkQ does when a processing task is too big, that means it has way too many events in it, is that it will see that it didn't fit, and then it will split it and then retry the parts and then keep doing this splitting until either it cannot be split anymore or we reach a maximum, which I think the default is 5. Yeah, the default is 5. Now, for these examples, I'm going to use a slightly modified basic test processor, which the only thing it does is to increase artificially the memory that the task use. And this is just for show. So I'm going to read our new processor. One thing that now we have to do is that since the processor I'm using, the source of that processor is not part of the coffee distribution, we have to tell WorkQ that it needs to send this source file together with the tasks. So we do that here in this WorkQ executor parameter, where we just give a list of extra source files that need to be sent. For single file processors, as in this case, or accumulators or things, or small data, things like that, this works really well. If you need to do more, like a more complicated environment, I will show you how WorkQ can do that too, like send complete conda environments. And the other thing I'm doing here in this example is setting a chunk size big and a memory like ridiculously low so that the tasks fail. And as the tasks fail, they are going to be split, and then we will observe the change in the chunk size as the example runs. Also, I set my workers so that at most 2 tasks run concurrently once we find the correct chunk size. So we will see that some of my tasks are running. I start to get errors because they don't fit in the resources that we specified. Eventually, you will see this counter to go up because they didn't fit. We will see, right, so at least 2 tasks have been exhausted. That means that 2 chunks of events have been splitted. And after the split, the minimum chunk size that we have seen is this value. Now, usually if you see this kind of behavior is that probably you want to rerun your workflow with a new chunk size. So this is great for exploring what are good chunk size given the resources that you have. It's also a lifesaver if only like a handful of tasks need splitting, then this will make the whole run work for you. But again, it's not like the most efficient way of running. The other thing we can do is rather than wait for things to fail, is that we can tell, and then you get a bunch of debug information in case you want to see which task failed. But one thing we can do is, rather than have a fixed chunk size, we can tell the work queue executor a target resource utilization that we want, and then we can let work queue find a chunk size that will fit that resource without going over. So in this case, I set a small number of events per task initially. I said that I want each of the processing tasks, not to use more than ½ GB. And then I tell Coffee, please adapt my chunk size to fit that target memory. So what you want to pay attention in this next example is how the current chunk size goes up. The maximum memory sync also goes up to fit the target that we set. So we wait for the worker to connect. And as you see, we are submitting tasks very slowly because my current chunk size is very small. Eventually, worker is going to realize that that chunk size is too small, and then it increases it. And in this case to 32K. And eventually the largest scene memory will be close to the 500 megabytes that we set.
Ben, I know that you only have 2 more segments in the notebook, but I think we should probably try and be wrapping up so that we can still make sure that we have time for a break.
Oh, great. Excellent. Yeah. So, right. So let me, yeah. So as you see, probably you also don't want to use this dynamic mode all the time, but it's great for exploring your new processors and new resources. And then once you find a chunk size that works, you want to set that forever, at least for the rest of the runs. So in the interest of time, let me switch ovens, so to speak. So let me. One of the things that we have been doing so far is setting the board in a fixed way, and that's kind of not very scalable. So one thing you can do with work queue is to give the coffee run a name. That name and the board is running gets registered in a catalog, and you can run your own catalog server, or you can use the one that we run all the time at Notre Dame. And then workers can connect to that catalog, get the name, and then connect to the manager. To do that, we usually recommend to set a password that gets shared between the work queue executor and the workers. So as you see, it's just a matter of giving a name, the password, and everything else remains the same. The other thing is the factory now needs to know the name of your manager. And the other thing I wanted to show you is, so I show you how to send a single processor file with the tasks, but sometimes you want to have the full environment, so you cannot install Coffee at the execution site. Together with work queue, we have a tool called Poncho Package Create, to which you define a specification, which is actually the same as a Conda specification. We write that to a JSON file. And then we can feed that specification to our tool, which then creates a tarball that we can send together with the tasks. And this tarball gets sent and expanded only once per worker. So it's efficient. And one thing I'm going to skip, but just so you know that, I mean, of course we can do is to run the factory outside the notebook so that you can have your manager running in one machine and the factory running in a front end on an HPC, for example. And I think that's all I have. So if you have any questions, I'll be happy to answer them.
Okay, great. Thanks very much for the nice talk. I think in the interest of time, we're going to just take one question now, and then we'll go to break and we can migrate everything else. So let's take Nikolai's question of how does work queue compare to Dask?
So one thing that in terms of the executor is that for coffee, we are more, I think we are more integrated with coffee, in the sense that we are more dynamic in the way we are creating the tasks. Right now, how the Dask executor works is that coffee gives the whole graph of tasks to execute to Dask, and then they get executed. And that's just a matter of how the executors are implemented right now. Like, I don't think there is no stopping, modifying the Dask executor so that it can do all these things that we are exploring with Workio right now.
Okay, great.
Yeah. And just to answer Oksana very fast. Yeah, so actually here at Notre Dame, the CMS group uses always the Workio executor. So I don't have the numbers right now, but it's in production here right now.
Thanks again, Ben, for this super nice talk. And right, so we are now going to go to break. We're normally scheduled for a half-hour break, but I think in the interest of time, to try and make sure that we keep the second session going, let's downgrade that break just a little bit. So let's try and aim for a 20-minute break. So let's come back here at the half hour. So talk to you soon. Okay, so it is the half hour again. So in the interest of trying to keep to the schedule, we're going to go ahead and get started. So the first talk we have in this second session today is about data management with regards to ServiceX used in Atlas workflows. So I'm going to let our speaker take it away.
Can you see me and my screen?
Yeah, we see the browser view, which is like probably fine. It's not like full screen, but it's still good.
Okay, so so my name is Kyung-won from UT Austin, and today I'm gonna talk about data management package for the novel data delivery systems of full ServiceX, and also want to talk about some of its application, and especially to that I'm working on, which is Atlas Run-to physics analysis. So let's start with ServiceX. So for the people who might not familiar, what is ServiceX? So ServiceX, it's not a simple to explain, but I would say the main property of ServiceX, it's a service to quickly access a fraction of large data on the grid. So let's assume that if an analyzer want to see a distribution of a variable or a column or branch from a range of a raw data on the grid. So far, one needs to submit a grid job to run over all those files on the grid, and then generate some histograms, and then download all the histograms, and then see the distribution. Or one can download all those files to the local machine, which is not so trivial. So ServiceX essentially provides some nice alternative to access this data rather quickly. So ServiceX itself is deployed in a Kubernetes cluster, and usually it is co-located with a data center or enough large cluster to provide enough high network bandwidth from the data center. So Kubernetes, if you're not familiar with Kubernetes cluster, it's like a container orchestration system, like a Docker container. So for once ServiceX, what ServiceX does is it essentially spawns so-called transformer pods to read columns and also filter events from each files from the data center in parallel. And these transformer pods they are scaled automatically using Kubernetes auto scaling feature. And once all the outputs are generated, and all those outputs are written to object store inside Kubernetes cluster, and then it delivers to the final destination as soon as it becomes available. And so the transformers are essentially the key object of the ServiceX, and they are at the moment separated by the input data format. So at the moment, ServiceX supports two types of transformers for different data formats. So one is root transformer, essentially for flat root table. So something like CMS Nano AUD or any analysis flat root table. And the other format is Atlas XAUD transformer for Atlas XAUD data. And since ServiceX, this transformer is really some core microservice to read and do what you want. So at the moment we have only two kinds of transformers, but also other types of transformers under development, and it includes some some transformer for non-LHC high-energy physics experiment. So yeah, now I want to talk about the language that need to be passed to the transformer, like what I want. So the language it uses is so-called FuncADL, Functional Analysis Description Language. And this is a query language that these two transformers basically understand. And it is primarily for filtering events and select columns, but it also actually is for some aggregation or adding new branch. And this talk is not, primary focus on the learning or these new languages, but details on the grammar or the syntax of the FuncADL can be found from the talk by Mason at last year PyHEP, and I think here. But basic operators of FuncADL is essentially also shown, will be shown in my notebook, will be select and where. Select is essentially used, I use for select columns, select branches, and where is basically I use to apply cuts. At the same time, there's another wrapper package for a familiar experience for the users. It also supports root Tika syntax, which is, I guess, more familiar with many people. So it supports basically many different kind of basic expressions like arithmetic operators and logical and Laplacian and ternary and mathematical functions. But the limitation is it's at the moment is only compatible with a root flat entable, essentially root transformer. And also, since it doesn't know the branch is whether it's a vector or scalar in the bands, the cuts can be only applied to a scalar turbo branch. Now I want to talk about, so far I've been briefly explained what is service X and where we can find service X. So at the moment, here I listed available service X endpoints you can access or you can use. So at the moment, we are primarily for Atlas or CMS experiments. So for Atlas experiment, we have one for root entable and the other one for XAUD. And for CMS, we have in Kafka for flat entable, essentially CMS nano AUD. And there's one for not that is open to to anybody to access, which is a CMS, which is not CMS Kafka open data endpoint. And here I differentiate the type into standalone and Kafka. Basically, standalone is it is secured by own authentication system. So you need to go to this web page and ask for a permission or ask for a token actually to access this service X endpoint. But standalone endpoint is once you get this token, you can access from anywhere. And for Kafka, at the moment, it is integrated into Kafka facility for CMS case. And this facility itself is secured by some authentication system. So you don't need any further token to access internal endpoint, service X endpoint in this Kafka facility. But this service X endpoint is not exposed to outside. And also for different type of input data and also for the location at the moment, for Atlas endpoints, University of Chicago Analysis Facility is the main provider, and CMS endpoint is mostly deployed to University of Nebraska-Lincoln, and they are all well maintained. So Service X endpoint, except the open data endpoint, it requires a YAML file to access the data, because they are experimental data, so they are restricted to only the member of the experiment. So, but this YAML file can have multiple endpoints, maybe not in many cases, but if you want, like for if you are Atlas member and you want to access XAUD and UMROOT and XAUD and UMROOT endpoint at the same time, you can list many endpoints at the same time. And the structure of the file is like this. So you can use one of these file name to containing the access information. So you need to, for the API endpoint, you need to give the name of each endpoint and endpoint address. This should be the name of the endpoint here. And for experimental, for Atlas, you need to provide a token and the type of the endpoint. And one nice feature I want to mention before I move on to the data binder is ServiceX front-end library supports local data cache. So all your ServiceX queries and also data are basically stored in the local temporary directory by default. So if you make the same query on the same data, it doesn't propagate the service request to the upstream or to the ServiceX backend, whether it pulls the data from local cache. But the local cache itself is unbound, so it will grow as you fill up. So you might want to, or you need to essentially change the cache path. Otherwise, it can blow up if you do in your local machine. So you can specify your cache path within this access YAML file. So let me move on to the data binder. So data binder is a Python library, essentially for easy manipulation of ServiceX delivery requests and also easy handling of delivered data using a single config file. So all you need to use ServiceX is essentially you need to have the ServiceX YAML file to access the ServiceX endpoint and also specify which endpoint you want to access. And you need to, this ServiceX data binder. Actually, ServiceX team was planning to have another open data endpoint for a standalone type of open data endpoint, but we don't have yet, but I will update this notebook accordingly. But you can actually go to this copy open data the Casa to follow all this notebook. Okay, let me import this data binder. So here is a workflow with Service data binder. Once you have this access file in place and also installed data binder. So a user writes a config file for data binder and make ServiceX delivery request from the notebook or any other terminal CLI. And then ServiceX backend essentially look for input data sets written based on the config file and retrieves all the input files from the data center to ServiceX front end and ServiceX backend. And then based on your query in FunKD or TCAD, it basically generates code to filter or to select columns, and then transform paths are generated to process each file. And at the basic or default setting, it generates 10 paths at first for each ServiceX request. And as I mentioned earlier, this Kubernetes cluster scales up transform paths automatically. And then all the outputs are written into object store inside Kubernetes cluster, and then download outputs to the local cache, essentially, local cache directly asynchronously. And then ServiceX data binder copy files and move things around to the final destination. And what is being done by your user is you need to write a config file and then ask for delivery. I want to do simple use case demo. Let's assume an analyzer simply wants to see an electron PT distribution from a large data set on the grid. And let's then write a config file. There are two types of blocks. One is general block and sample block. In general block, you need to specify what is the name of service backend, which you specify in this XF file, and then the output directory, and also what type of format you want to get as output. It supports Parquet or root for umroot transformer. And this is the name of the output YAML file, which essentially containing all the outputs in dictionary of all the output file paths. And then you should have sample block. In this block you need to specify the name of the sample, and also in this example I am reading CMS open data converted to flat data pool by Alex, and I'm going to use about 50 files, but since it's open data, I read from using XRT protocol, and it amounts to about 10 GB in total. Since it's demo, I use rather small files, and I need to specify the tree name of this entity, and then the query that I want to pass to the transformer. Let's have a look at the config file. So as I mentioned, here I'm using umroot endpoint at the moment, since we don't have a standalone open data endpoint at the moment. So I'm using one for Atlas, and the output directory name, and I want to get the outputs in format of Parquet, and I want to write a YAML file containing all the bypasses. And the name of the data set is ttbar, and here I list the 50 files. And as you can see here, I'm reading from UNL. So the files are sitting in UNL machine, and I'm using UCAF. So the ServiceX is deployed at University of Chicago analysis facility, and the files are sitting in UNL. And then the events is the name of the tree, and I wanna branch electron PT, but I wanna apply cuts. So for the events where there are more than 5 electrons. So let's write this file. And then this data binder load this config file, and I can ask for delivery. And then it is delivered to my local machine, since I'm learning this notebook in my local machine. And my laptop is sitting in South Korea, so it might take a while if I pull down whole data set. And there are 2 progress paths, as you can see here. So one is for transformation. So there are 50 files in total, and 18 are done. And I downloaded 22 files. And you can see, it already flipped away, but sometimes it doesn't refresh accordingly. So download can be higher than transformed. So they are downloaded and also delivered to my laptop. And in addition to the progress bar shown before, you can also monitor this status of transformation in the dashboard. Essentially the web page that I put here for standalone service endpoints. And then now we have the output. let's have a look what we have from output. So this output is Python dict. So this has a key of TT bar, and in the TT bar it has key of events. So for the tree name of the tree, and then there are 50 files delivered. And let's make a plot out of these files, these delivered PyHEP files. Okay. So yeah, here you can see, since I require more than 5 electrons in an event, so there are 6 electrons, for example, and number of events, essentially, delivered 14K. And I can, simply make a histogram out of that. So this basically demonstrates that it's much faster and easier to deliver a fraction of data with a selection of column and also filter events and see what it has. And as I also mentioned, this 1KDL expression also can be replaced by Rutica syntax. So if you are not familiar with this 1KDL syntax, we can use instead of 1KDL, we can use filter and column. Basically, columns is the select of columns, and filter is the cuts you want to apply. So I basically write the same config file for the same data sets, but instead of 1KDL, I use filter and columns. Let me ask delivery of the data, and it is done because it doesn't make a new service X delivery request to the service X backend, or rather it gets the data from the local cache, since it is the same query on the same data set. So if I make a change here, let's say, and then now it's different data set, not a different data set, it's different cuts. So it needs to make a new service X request and so on. So yeah. And what I showed for this demo is essentially using open data. So it uses Rusio, not Rusio, it uses XRT files. So it had to be separated by commas at the end here. So it's not so, it doesn't look clean or nice, I would say. But if you, it's more, it's more practical use for the experimental data behind the NAS. Thus, Rusio DID is I think more typical type of data set. Also, it is supported by service X. So let me run Rusio data set. This data set is another CMS open data converted to flattened pool, and it's amount to 11 gigabyte and 114 files. And the files are sitting at PNL and Munich in Atlas storage, but it is now pulled to UC University of Chicago AF facility service X deployments. So you can see how fast it runs. So the transformation is already done, almost done, and it is primarily due to download to my local machine. So another use case is if analyzer want to exploit service X for physics analysis, it gets more complicated, but we know there are really diverse ways to get results from large data set on the data center. So every analysis and also has own problems and even various needs within an analysis team. So I'm trying to show some examples based on this schematic. So what kind of possible workflows analysis workflows with ServiceX. So first one is just delivery of root files. So this is minimal change, I think, to the traditional workflow. So an analyzer only use ServiceX, just get selected and filtered branches in the root format. So, and then perform all the analysis, all the subsequent analysis with familiar tools like C+ event loop. And the other, this is in this dash line using only ServiceX for root files, and then doing whatever you already familiar. And the other thing is ServiceX plus Kafka thing. This is what I am basically working on. Is a bit more toward to Python ecosystem. So ServiceX delivers Apache Parquet files essentially containing occur arrays, and this core analysis is sitting in Kafka framework. And it just, I use Kafka framework only up to making histograms, and we, in our analysis team, we want to use the same statistical analysis tool to produce final results. And final workflow can be everything in Python ecosystem, ServiceX, Kafka, and cabinetry essentially, and do PyHEP to produce the result. Let me quickly show deliver root files. Deliver root files is very simple in Umroot for the flat entity. So you just need to change the format from Parquet to root. And this this config file contains 3 samples: data, entity bar, and double jets, and also with the same query. But the only difference maybe is this root file. And I have 3 different data sets here. Let me write this, and that's for delivery. As you can see here, since now I have defined 3 samples, ServiceX requests are generated basically for each sample, and they are all run in parallel. And also download asynchronously. This is a bug from TQDM. So they are done. And now let's have a look the output files. So now the output have 3 keys for each data, each sample, TT bar and double jets and data. And and since we are in Python world, we need to use Umroot to open root files. Let's have a look at first root files in this TT bar sample. And you can see this has a key of the tree name or events. And this event basically has electron PT delivered. And this n electron PT is automatically added since we use Umroot essentially to make this root file out of Parquet. And if for my workflow essentially, which is ServiceX plus Kafka workflow, I use Parquet file since Kafka understand Parquet very well. I don't need to convert that Parquet to root file. So the only change is to Parquet here. And if I ask for delivery, since as before, since it's the same query, so it gets pulled from the local cache. So, and as you can see here, if I change just one line, one query of one sample, like this is, I change only for data here, and then it pulls, it makes another new delivery request only for the changed or updated sample. So this is, really, easy way to, maintain what your data sets stored in your local and what you want, or whenever you want a new column or whenever you change your data set, you only need to change all and pull down all the that new data to your local machine or your working machine. So in my workflow, this is actually the code snippet I took from my code. So yeah, as I'm not using work queue. I actually download Service Act delivered data to our UT local machine, which has enough power, about 40 cores, and I run just a Future Executor to run this. And this file sets are essentially what I got from Service Act data miner. So it is really interfaced to copy very nicely. And I want to end with advertisement actually. So ServiceX plus Coffee and Cabinetry workflow, or AKA PyHEP analysis grand challenge workflow. It's really, really fascinating. But yeah, there will be a talk by Alex Hell tomorrow morning or after night, depending on where you are. So yeah, please go to this this talk, and I'm sure Alex talk gonna be very interesting. And I wanna emphasize, I think I have 20 seconds, but I want to end my talk with that. Since my demo or my notebook is primarily for Atlas, maybe CMS, but ServiceX itself is really running transformers in parallel and very easily. So this transformer essentially can be a transformer for any kind of data format. So for different data, different experiments, or whatever, depending on your need, it's really, versatile, I would say. Yeah, that's all I want to say. Any questions?
Okay, great. Thanks very much. This is a great talk, and I think it's really powerful to see these live demos like you were doing here. So thank you so much. This is excellent. In the interest of sticking to time, though, I'm going to suggest that we take all the questions from Slido and move them to Slack. So if you wouldn't mind, I know we have at least one or two. So if you wouldn't mind just hopping over and answering them on Slack, that'd be much appreciated. Okay. All right. So next up,
distributed analysis.
Sorry, say it again, Jim.
Which channel? Distributed analysis.
Sure. Let's go with that. Okay, and so next up, we have Danny, who's going to be talking to us about EOS. So Danny, take it away.
Thank you, Matthew. Thank you for the opportunity to present to you EOS, a software for flavor physics phenomenology, which I'm presenting on behalf of all of the EOS authors. Thanks also for accommodating me on short notice to move the talk around a little bit. I appreciate that very much. So let me move the faces out of the way. So yeah, EOS is a software for a variety of applications in flavor physics. It's written in C++, so ordinary it wouldn't fit in here, but it provides an interface to Python. And actually the Python interface is the recommended interface to use EOS. And we highly recommend to carry out all analyses with EOS within a Jupyter notebook, just like this presentation is one. And if you're interested, you can find the list of all the contributors behind this link here. Once I upload it to the Indico. Okay, so why can't I move? I can move on. Very good. So EOS was written with 3 use cases in mind. First, to produce publication quality theory predictions for flavor observables. Second, to infer theory parameters from a set of likelihoods. It's actually an extendable database of likelihoods that comes with EOS. And which you can extend on your computer in addition to what is provided via PyPy. And third, to produce high-quality Monte Carlo samples of flavor processes, for example, to conduct sensitivity studies. So what follows is a very condensed presentation of these 3 use cases, and the complete tutorials are available online behind this link here on the EOS GitHub page. Very good. Some preliminaries. Of course, if you want to follow this, you need to install EOS. So it's as easy as running pip3 install EOS HEP, because EOS had already been taken. Not too surprising. If you want to try it, you will need Python version 3.7 or higher, which should not be hardship. And to load EOS into your notebook or any other Python interpreter, simply import EOS. And let me do that right now. That worked very well. And for later use, we will also need NumPy. So I seem to have forgotten to clear all the outputs, but let me do that nonetheless. Very good. So with the preliminaries out of the way, let's get into the first use case, the theory predictions and uncertainty estimates. So EOS was built to provide accurate theory predictions of a large number of flavor physics observables. And this, of course, includes determinations of the uncertainties, which we do in a Bayesian framework. So first, let's start with what these observables are. And to get an idea, you should inspect them. EOS features more than 1,000 pseudo-observables that can be readily predicted. And when we're writing pseudo-observables, we mean basically everything that EOS predicts is considered an observable, even though it's not a physical observable. So pseudo-observable that can be predicted are, for example, certain hadronic matrix elements, so-called form factors, which are functions of kinematic variables, which have a common interpretation, but that are really not physical observables. Nevertheless, they can be obtained, for example, from lattice QCD, from continuum QCD methods, and they sometimes need to be averaged. They need to be checked against each other. So we count them as a pseudo-observable. The total list of observables is available online behind this link or interactively within a Jupyter notebook. So let's actually try that out. What I'm doing here is I'm constructing the observables class, and I'm filtering. I'm filtering for a D-meson in the process and for observables that include BR for branching ratio. So let me do that. This is the output. Not very informative right now. It says the observables in a number of semi-leptonic B-hadron decays. But because this list is so long, what we have done is we have by default collapsed everything. And if you click on it, you can see a little bit more. Now the rest is almost out of view, but that doesn't really matter because we can focus on these two, which will be used in the remainder of this presentation. So B2DL new is the process that I want to focus on. BR is the integrated branching ratio. You see the nice mathematical symbol that's usually used for it. You see what kinematic variables it requires. And for the so-called, well, let's call them power users, you see all of the options that can affect such an observable. These options are consumed by the observable upon construction and cannot be changed thereafter. And they include, for example, the choice of model, which is defaulting to the standard model SM, but can vary to or can be changed to, for example, CKM, which is kind of the standard model, but all CKM matrix elements will be promoted to independent parameters with 2 real degrees of freedom. So you can fit absolute value and phase of each CKM matrix element. Or WET, which stands for weak effective theory. So if you're hunting for physics beyond the standard model in these processes, this gives you access in a model-independent way to the effective field theory couplings that can modify your processes beyond the standard model. Similarly, we can open up the form factors. So hadronic form factors describe these processes since they are genuinely non-perturbative quantities. There are varieties of parameterizations that can be used. Basically, all of these names that you find here are available online in the documentation in a list of references. You can click on them and see what these form factor models are and what parameters they have. Right, so as I said, these two observables, the latter one, the differential one in the variable Q square, which is the invariant mass of the lepton-neutrino pair, will come a little bit later. Let's focus mostly on the branching ratios and collapse this. Very well. So how do you construct and evaluate an observable? EOS uses these observable objects as the basic building blocks for all types of analyses. They can be interactively constructed in a notebook as follows. So to make an observable, you run observable make. You need the name. You need a set of parameters. If you make several observables, you can share parameters between them. This is how we do the fits, by shared parameters object. You need to supply a number of kinematic variables. They're encapsulated in a kinematics object. And you need to provide an options object, which can be empty, but in this case is pre-populated with an option that sets the lepton flavor to a mu lepton. So if you do this, very well, we get the following output or display for this object called OBS. It's a B2DLNU branching ratio observable. That's no surprise. The kinematic variables as we set them and the current value of the observable. You can evaluate it using the evaluate method. You can inspect it further, but I don't have the time to do that right now. All of the methods that affect an observable are listed in the online documentation. So as I said, we need this set of parameters, kinematic variables, and options. But for more complicated, more advanced applications, they will likely be provided in a more structured way. Then, now that you have an observable, typically what you want to do is you want to visualize it. And EOS provides some plotting framework for that based on matplotlib that can illustrate any number of observables that you're interested in. And it accepts a dictionary like this. So what you see here is that on the x-axis, we put the q-square variable, this kinematic variable, in a certain range. On the y-axis, we put the differential branching ratio. We put the legend somewhere convenient. And we plot two plot items, contents items of the type observable. Sorry, here. And the observable that we're plotting is this differential branching ratio for muons and for tauns. And this is what comes out of the whole exercise. Of course, this is a typo that should have been figure. So if you run this and you want to modify your matplot figure for some reason afterwards, you can access the matplotlib objects which are returned like this. Very good. So we have illustrated two observables. What else can we do? Well, we can estimate the theory uncertainties. Just having these narrow curves here is not, well, it's not quite all that we want from it. We want to produce some bands that show us the theory uncertainties. Again, we default to Bayesian statistics to determine the theory uncertainties. And to do that, we define our posterior using the EOS analysis class. There you specify your set of priors, your likelihood, and therefore overall your posterior. And it's quite short. What you need to do to create any EOS analysis object, you need mandatorily the priors, which is a list of prior specifications. They contain their parameter name, min and max range, and the type. In this case, uniform. In the documentation, you can see more than uniform priors. We have Gaussian priors. We have specific theory priors that use a Gaussian distribution for logarithms of your renormalization scale, and so on. But you also need the likelihood. So in this case, it's a list of constraint names. These names can be found online in the list of constraints, or you can look them up with eos.constraints in a notebook. These are two constraints by the HPQCD and Fermilab NERC collaborations for these B2D semileptonic form factors. Okay, so let's create that object. Very well. What we can do now with this object is we can sample from its posterior. The parameter samples that we obtain will require some Monte Carlo sampling. The simplest approach that EOS provides involves Markov chain Monte Carlo sampling, so Metropolis Hastings, but more sophisticated algorithms like population Monte Carlo and nested sampling are available, i.e. the interface to external software that implement these algorithms is available. So we're using the PyPMC package for MCMC and population Monte Carlo, and we're using Dynasty for nested sampling. Posterior predictive samples for any number of observables can be obtained in parallel to the posterior samples. If you're defaulting to the Markov chain Monte Carlo. And it looks like this. So we're producing some Q-square values for this decay B to D tau nu in the differential branching ratio. We make a number of observables in this very Pythonic form. We share the same analysis parameters for all of these observables, but they have individual kinematics. And the tau is selected for the lepton flavor, the BSZ 2015 parameterization for the form factors. And then we go about it. We sample from our posterior and tell it, oh, please also do some posterior predictive distributions for the observables, especially these observables. We obtain a total of 5,000 samples, and then we're done. Quite fast, very nice. Using these samples, we can now illustrate the posterior prediction and therefore the theory uncertainty. And it looks like this. So instead, the plot setup with the X, Y axis and the legend is the same as before. However, the contents has changed. There's a single content item now, which is not of type observable anymore, but of type uncertainty. The other items for this are also documented online in the, on the web page. The change that we have now is that we provide some data in form of the samples of the posterior predictive samples and the corresponding Q-square values. And we can plot it and get this nice band corresponding to the 68% uncertainty envelope of our prediction. Very good. Let me continue with a second use case, parameter inference. So as I said before, EOS can be used to infer parameters from either experimental or theoretical likelihood. It really doesn't care. It treats them all the same. And again, it defaults to using a Bayesian framework. So what we do is extending the analysis that you saw before by adding two experimental likelihoods for measurements in several Q-square bins of the branching ratio for B0 to D plus E minus nu decays or mu minus nu decays. They're coming both from this publication by the Bell collaboration, and as for all these names, you can look them up in the list of references where you find a hyperlink to the preprint and to the publication. In addition to the two experimental likelihoods, we also add the CK matrix element VCB, or rather its magnitude, to our list of priors. The full list of constraints, I said that before, but I hadn't written it down. I do it here. The full list can be inspected interactively using eos.constraints or via this hyperlink. And let's set up the posterior. So as I said, we are now at one prior and two pieces of experimental data to the likelihood. So this is what our construction of the analysis looks like. So this first line here is new. It sets some global options that affect all of the observables that are used within the analysis. So all of the observables that are created as part of the likelihood will be affected by these options rather than providing them individually. So all observables use the same model for, the same parameterization for the form factors and the same model, this CKM model. So all observables are in principle sensitive to the magnitude of VCB and all of the form factor parameters as before. And these two pieces of experimental data have been added. In addition, we set the VCB value to some kind of sensible initial value before we proceed. Very well. The next step is to optimize the posterior and check if we obtain a good fit. So we do this by defining or obtaining our best fit point using analysis.optimize. We display it and we display a goodness of fit summary. And that's also quite quick. We get this value of 41.9 times 10 to the minus 3. The form factor parameters are very close to their prior values. For the goodness of fit summary, you find for each constraint the chi-square value, if applicable. EOS supports multivariate Gaussian likelihoods, but it also supports likelihoods that are outside of the family of Gaussian distributions. For those, of course, we do not list any chi-square value, and we cannot include these in the total goodness of fit summary. So for each constraint, chi-square, the degrees of freedom, and the p-value, assuming that there were no parameters. So all of these would give a reasonable fit. And taken together, we find this total chi-square for 26 degrees of freedom, corresponding to these numbers of observation minus these now 6 parameters, giving a p-value of 60%, which is a good fit. We're very happy with that. Very good. The next step is to determine the uncertainties on our fit parameters. To that end, we draw samples of the posterior PDF. And again, we're using Markov chain Monte Carlo as the least sophisticated method available, because this is a very easy analysis with only 6 parameters. What we're doing here is we're initializing our random number generator. This is optional. I wanted to just showcase it here to make your analysis reproducible. We are obtaining the parameter samples from EOS analysis sample. We take 5,000 samples with some configuration for adaptive pre-runs, which filter out only take every 5th step along the way, and a total of 2,000 steps per pre-run. We're also starting our Markov chain at the best fit point that we obtained earlier. You can see that the Markov chains adapt quite quickly, and for the main run, we get an acceptance rate of 25%, which makes us quite happy, and we can proceed to visualize what these results look like. And due to the time constraints here, I will only do that for the one-dimensional marginalized posterior for the VCB parameter. So to do that, we're using the plotting framework again. We put VCB magnitude on the x-axis, put the legend at a convenient position, and show both the samples that we obtained in form of a histogram and a kernel density estimate of the samples. We do that right now, and you can see our histogram and our KDE agree very well with each other, as they should be. We get a value of 42 times 10 to the minus 3 plus minus roughly 1 times 10 to the minus 3, and we can actually investigate that a little bit further by taking the mean and the variance of our samples and plot them, and you see, yeah, 42, that fits quite well, and I was overestimating the standard deviation a little bit. Excellent. So let's come to the last major use case, Monte Carlo simulation of pseudo events. EOS can provide these Monte Carlo samples of a variety of flavor processes. And these have been previously used to conduct sensitivity studies in the context of experimental analyses. So to see the full list of signal PDFs from which we can sample, this EOS.signal PDFs inspects them interactively within a Jupyter notebook. So let's do that. Again, I'm applying a filter because the total list would run out of the boundaries of my presentation or screen real estate. So there are 2 of the signal PDFs. We're going to concentrate on the first one, which is the one differential distribution. It's differential only in Q squared, this dilepton invariant mass, rather than the full differential distribution, which is also sensitive to the cosine of the helicity angle between the lepton and the neutrino pair. Very well. So using this signal PDF as an example, we're actually splitting that into 2 examples. We want to simulate final states with a muon and with a tauon. So we set up some kinematics for the muon case. We produce our signal PDF from this name, a set of parameters, our kinematics, and the default options, and sample from it using sample MCMC. We obtained a total of 20,000 samples from this process after some adaptation to our Markov chains. We do so with a pre-provided random number generator. So again, this will be a reproducible step. And we repeat it for the tau lepton, for which we need to adjust the kinematic range to the minimum, the left end of the kinematic range to the tau mass. Again, reproducible, very quickly obtain these tau samples. And in the next step, we visualize them, and we're comparing them with a true signal PDF, which is available. So in our plot, X now shows Q square. On the y-axis is the PDF. Legend is conveniently located, and we have 4 plot items: 2 histograms corresponding to our muon and tauon samples, and 2 plots of the analytic PDFs. Again, for the muon and the tauon sample of the type signal PDF, and selecting the signal PDF simply by the name. We can provide options, as I said previously, by simply appending them to the name of any signal PDF or observable. And doing this produces this nice picture below, where you can see that our Monte Carlo samples very neatly reproduce the shape of our analytic expression. Excellent. So what have I not shown to you today? An in-depth presentation of EOS would have taken more time than allocated for this introduction. There were 2 major elements that were not shown. One, to provide that EOS provides code for a number of what we call tasks that are common to all Bayesian analyses. This is existing and working code. It has been successfully used for a few projects already. However, the documentation is not complete, and we are working on that. The tasks have a very well-defined way to store and share their data. The analysis description is common to all tasks and is done in terms of a single YAML file. So if you're interested in that, we have some preliminary documentation for that, and I can share that with you. Tasks can be run both within a notebook and on the command line. And the latter is quite important if you want to do batch jobs in a cluster environment. Not all of the analysis that you do with EOS, as I've shown you today, not all of these analyses are this quick. Some of them take hours, days, and if you do that and want to do that in a cluster environment, the command line tools which use the tasks framework are what you're looking for. The second major item is that we are in the process of making our analyses reproducible. So beyond recording the priors, the options, the likelihoods of our analysis, we also want to record the settings. That is the number of pre-runs, the number of samples per pre-run, the overall number of samples returned for the whole analysis, and so on. And we're making progress in this regard, but this is not quite complete. And with this, let me come to my conclusion. This was a really short but quite dense summary of the EOS use cases. More detailed tutorials are available online in form of interactive Jupyter notebooks. The documentation, the link you see here, includes non-interactive HTML versions of the tutorials as well, which are more extensive than this. We are always happy to extend EOS by adding new features, observables, PDFs, and so on. If you're interested in that, let us know. The best way to do that is via our Flavor Physics Discord server, where we also provide support for EOS. If you do join via the link behind the invite link here, feel free to drop by in the channels EOS or EOS Dev. And we are very welcoming to all new users or prospective contributors. So thank you very much for your attention. And if there's time, I'm happy to answer any questions you might have.
Yeah, excellent talk. It's always really nice to try and to see these sorts of tools, and it's also nice to see tools that are using Bayesian techniques. So I think we have time for at least one question, maybe 2 if we're fast. So let's go to Slido. There are some comments that I think are generally useful, but I'm going to go to Nick Smith's question first. And he asks, Is the full dimension 6 Warsaw basis of SMEFT operators available? And have you tried any global fits? And if so, how well did they scale?
Okay, so this assumes that we're using SMEFT at all, which we're not using. For flavor physics, SMEFT is not the best choice of effective field theory. Instead, the weak effective theory is the theory of choice. And this effective theory lives at a low scale of, let's say, a few GeV. Of course, it can be matched onto SMEFT. There's a paper which does this matching at the one loop level by Wouter Dekens and Peter Stoffer. And there are other Python utilities that you can use to interface with EOS to obtain flavor physics constraints on the SMEFT coefficients. And no, we've not tried a global fit yet, because the total number of SMEFT operators is, I think, in a flavor anarchic setup, it's slightly less than 2,500, and you simply don't have enough complementary flavor constraints to achieve that.
Yeah.
Maybe a small...
Nick's, oh, sorry, Nick's connected. I'll let him talk. Sorry.
A small follow-up. So I guess this means that you can't do any running of the scale up to sort of like energy scales that we're probing SMEF models and CMS analysis.
No, this is specifically for low energy flavor physics. So BDKs is kind of the highest scale that we're accessing. If you want to use this in connection with a SMEFT analysis, I recommend to use EOS in connection with Wilson. It's a Python package that can match and run. So it can match from SMEFT to wet and run your parameters both in the SMEFT and from your matching scale in the wet down to the B physics scale or charm physics scale or strange physics scale, whatever you prefer.
Okay, cool. So there are packages out there to do the running.
Yes.
Awesome.
Yeah. Okay, so thanks again for that talk, Danny. Really, really nice. In the interest of time, I think we're going to move all other questions from Slido onto Slack. So hopefully you can answer some additional ones there. And
I'll have a look.
if we can also get you to upload your slides, that would be fantastic.
I will do that immediately. Thanks.
Okay, thank you so much. Okay, and so we just had a great question from Nick, and now we're going to be continuing to hear from him as he's going to be introducing us to CorrectionLib.
Hi there. Yeah, thanks for having me. Let me share my screen. So yeah, I'll be running this from my local computer, but in principle, this should work on Binder just as well. So yeah, what is CorrectionLib? The purpose of the library is to provide a well-structured JSON data format for a wide variety of like ad hoc correction factors that you might encounter in a typical HEP analysis, and sort of in a companion tool suitable for use in C++ and Python programs to evaluate them. And so we're restricting ourselves very narrowly to class of functions with scalar inputs and scalar outputs. And the main purpose of this this narrowing definition is basically we wanted to encapsulate the wide variety of different data formats and tools that were found within the CMS collaboration. This is where this tool was sort of born out of, is the need to condense all the different various end stage analysis scale factors into a common format so that it was more easily distributable and more easily reproducible, so that different analyzers could get the same results with the same inputs. And so higher level things like correcting Lorentz factors is out of scope. We're just focusing on scalar functions. So if you like in Python, the signature would be some variable number of arguments that are integer, float, or string type, and it returns a floating point value. And then, in conjunction, there's a C++ signature that looks something like this, using C++ 17 features like standard variant. There's many different kinds of function classes. I'll try to go over them a little bit briefly in this notebook. But basically, it boils down to multi-dimensional bin lookups pointing to multi-argument formulas with some restricted math function set, categorical Go maps like string or integer enumerations, some transforms, pseudo-random number generation, and compositions of the above. And with these set of function classes, we found it was enough enough richness of descriptive format that we can encapsulate basically all of the end stage analysis correction types that we see in the CMS collaboration. And so the collaboration is now moving towards describing all of its end user analysis corrections in this format. So the basic usage for an analyzer that's using the evaluator is basically you import some previously defined set of corrections from a file or from some string that you grab somewhere, and this is just a JSON file. There's absolutely nothing special about this file. I'm just going to open it just to show you what it looks like. It's just standard JSON with standard types, and this tool will read that in and give you a list of the available keys in the correction file. Each one has some various metadata like a name, a description, a version, and what the input and output types are. And these are all programmatically accessible through attributes of the objects. So you can see, for example, this correction called Gen 2 to Gen 1 has two inputs, one PT and one eta. You can probably guess what those mean. And then this other one has some various other inputs. In a little bit here, I'll show you another way to present the same information that's a lot nicer looking than this sort of programmatic access. Of course, most importantly, you need some way to evaluate it. And so in Python, that would be, for example, evaluating a correction like this phi mod correction, which you don't know what it is yet, but let's just say we know it has an input of phi and input q. And if I evaluate it with that input, so I get an output. And how to interpret that will depend on the metadata of the correction. The input types are strict in the sense that they aren't coerced. And this is sort of on purpose. So for example, if Q was a floating point number instead of an integer in the above example, I would actually get a runtime error that the input has the wrong type. And this is on purpose to basically make sure people are applying corrections properly to the proper inputs and just avoid bugs by catching them early. And you can see here, if I change it to 0, this particular correction doesn't have anything defined for the value of 0. And when it was made, it was decided that this should raise an error. We'll go into this a little bit later, but you can actually choose how to deal with out of bounds inputs. It depends on the case by case. Now, of course, evaluating it for single sets of arguments is not going to be terribly efficient in Python, although in C++ that's just fine. So of course, we also allow vectorized evaluation, where vectorized is in the sort of Python sense where you pass a NumPy array, and under the hood, it's doing evaluation in the C++ library efficiently. And so this correction called PT weight is being evaluated on a length 10 array of random inputs, and it produces a length 10 array of outputs. Currently, any NumPy compatible awkward arrays are accepted, but jagged arrays could be, for example, flattened and applied and unflattened. We're working still on making this work for any awkward array type. Awkward just recently provided some hooks into their API to make this a lot simpler, so we'll start to look at that soon. But for now, you can, of course, flatten your arrays, apply a weight as we did before, and then unflatten the array to get a jagged array if you need that. So that's all I'll say for evaluation for the moment, and kind of go into exactly how a new correction would be made. Correction Lib, separate from the evaluator, has a complete JSON schema that defines the expected fields and types found in the object. This is something we focused on early in the design, is to make sure that whatever file type comes out of this tool, that it can be completely described by a JSON schema. And so that did mean that some ways in which you would arrange the data look a little weird from a naive point of view, but to make sure that it is actually validatable by a JSON schema, we had to do this approach. And the complete schema is defined in the documentation. And then in the package, we actually use this tool called Pydantic, which is essentially a Python validation library that has a one-to-one correspondence with JSON schema in terms of support. So we're able to basically write Python classes that then get converted into JSON objects that conform to the schema. And as you build the classes, you can be assured that they conform or are coerced to be conforming to the schema. So here what we do is we make this simple correction object. This is schema version 2. We give it a name, a version, what the input is, and then what the output is. And then right now, for simplicity, the correction always returns a single value. It always returns 1.1, no matter what the input is. We'll see in a second how we can change the data to be more complex. This object could be manipulated in place to change the definition, to add new nodes to the data tree. And you can also convert it straight from the schema to an evaluator with this sort of shortcut expression. And you can see that no matter what I put in as my input, I'm always going to get the same output because that's the data that's defined. And now finally, we can see a much nicer printout through the use of the rich library. So this is much easier than the programmatic access I was showing before. You can see PT weight, which has no description. I could add a description up here if I wanted. And then it has a description of the inputs and output and importantly, what the output means. And this will depend on your correction. Sometimes you'll do a multiplicative event weight. Sometimes you'll do a additive shift to a quantity or what have you. It depends on the use case. So of course, the main point here is this data node that we need to fill in. And that becomes a root node of a tree of objects defining how the correction is to be evaluated. In the first example, it simply terminates at this node that says, okay, always return 1.1. But we can switch in many different node types. There's binning for 1D bin variables, where each bin can be itself any type. Multi-binning for nested 1D binnings. This is an optimization detail. We have category type for discrete dimensions. We have formula for basically arbitrary formulas and up to 4 real or integer valued input variables, sort of in the spirit of T-formula. Formula ref is an optimization where you have the same formula but many different coefficients, and this can be up to several thousand. There was a particular use case in CMS where there was a bin formula, basically a spline, if you like, that had up to 8,000 formulas. And so having this formula ref optimization saves a lot of space and evaluation time. There's a transform node to sort of rewrite input as you go through the tree. And then most recently, we added this hash PRNG. So a deterministic pseudorandom number generator that's useful for smearing like activities, which I'll show in a little bit here. So here's a bin correction where I just have, a binning with some edges and content. And you can see this is all in the data node. And you see when I start adding nodes, I get a bit more information in my output, like what the allowed range is and whether overflow is okay. You can configure the flow behavior. The flow could be either clamp, as in clamp to the nearest bin edge, error, or it can also be any other downstream node type. So you can even implement a whole new binning in the flow variable and have that, as the evaluation descends through that node, it says, oh, this is outside the boundary. Okay, evaluate this downstream node to decide what to do. And that's very useful for things like doing special handling of systematics when you're out of the nominal range. So you can see here, it just clamps to the highest value since I'm over the range. Okay, formulas. Formula support currently is a mostly complete subset of the root library T-formula class, but it's actually implemented in a standalone thread-safe manner. So this library is self-contained, does not depend on root or in fact any other library besides NumPy. the parsing grammar is formally defined and parsed through a parsing expression grammar library. For those of you that are interested in this, it's you might be interested in the details of how it's implemented. It allows very fast parsing of thousands of formulas encountered in, for example, spline correction types like I was talking about before. And we demonstrate here it's a very simple formula for some made up correction. And you can see now that the correction is getting more complex. You start to see, the description is getting quite large. So you have a category which is deciding this Q value, this charge that we were demonstrating earlier, and depending on whether the charge is 1 here or -1, you get a different formula. So one for, say, positive charge, one for negative charge. This is just a made-up correction. It doesn't necessarily correspond to anything that you might find in practice, but it demonstrates that you can write an expression and have it evaluate on a given input variable. And again, you get this nice rich representation, and if you convert it to an evaluator, of course it runs just fine. You can see right now, if I set the charge to 0, it'll cause an error because that was not one of the categorical values that I listed in my category node of the correction. But if I wanted to, I could add a default behavior. For example, I could return, say, 1.0 in a case where there was no category key corresponding to the input value for Q. And you'll see actually when I do this, the input here definition will change slightly. Now it says it has a default. So now if I run this, it should be okay with that and return the default value. Okay, so very often you'll want to convert straight from a histogram to a correction object. So what I'm doing here is basically showing that you can convert from anything that respects the unified histogram interface protocol. So it includes things like TH1s or anything in the hist package. Here I'm demonstrating creating some mock data in 2 dimensions, let's say a PT and eta dimension, and I fill it with just random, pseudo-random values. And so you can see there's these 2 data sets. Let's pretend, for example, it's 2 different generators, Gen 1 and Gen 2. And one has this PT spectrum and the other one has the other one. And we'd like to derive a correction as a function of this 2D variable such that, it reweights events from Gen 2 to match Gen 1. And so this is what this is doing. It's basically just grabbing the histogram's values, dividing them, and then setting it to 1 anywhere where we ran out of statistics. And then here I'm using a little shortcut to display it by putting the data back into a hist object and displaying it. And so you see that, here's what the correction value, the binned correction value looks like. And if we want to convert that to something that we can actually use, we can use this convert.fromhistogram utility. So first thing I do is I give it some more metadata like the name and the label. And then I call this from histogram, and then I give it a description here and also tell it what to do with the overflow bins. In this case, I'm saying it's okay if it's out of bounds, we'll just clamp to the nearest available correction value. And so now I have a correction, and let's see what happens if we apply it. So I'm going to generate some more mock data drawn as if it were from the Gen 2 distribution. And I'm going to use the hist library to fill from that mock data, but with a weight now, where I'm applying the weight that I just derived. And if you look now, you can see that the second generator after reweighting looks much, much closer to the first generator. They're statistically compatible now. I see that I'm getting close to my 20 minutes, so I might get a little brief here. Apologies for that. One thing you might want to do, it's apparent from the plot of the 2D correction factor above that we don't really have enough sample statistics to derive a smooth correction, right? You saw that this histogram doesn't really represent properly the ratio of the likelihoods of the events from the 2 different generators. It's an approximation, and it does do a decent job of correcting things, but you may want to do some sort of fit to that. And I've sort of imagined that this correction live could be a natural home for deriving, for including tools to help, create these sorts of fits, how to, like take some, empirical distribution and turn that into a proper, a proper model for how you want to do the reweighting. And so this is sort of the first tool in that library towards that end. And it's simply just an n-dimensional polynomial fit. And it allows you to basically take let's say the centers of the grid of bins that I just created in the scale factor histogram, and then fit those bin centers and their bin values with some estimate of the variance, and produce a polynomial that's degree 2 in PT and a degree 2 in eta. And so that's what this does, this ND polyfit. And it also includes a little bit of information about the fit result in the documentation of the correction. So you can see now I have this correction that is fit to the polynomial. The fit status actually was a success. It managed to fit. You see the chi-squared is reasonable, a little suspiciously good, but nevertheless, we can now apply this correction that is a order 2-2 polynomial to the input, and let's see how that does. And so this polynomial reweight in red, the plot's getting a bit crowded now. You can see that it also seems to make Gen 2 look much more like Gen 1. And maybe, you would hope that it has some better performance in the rarefied areas of the correction, because this is just a PT projection, not seeing the eta. So yeah, that's how you can, derive a polynomial fit. And I think it would be nice if this package could start to collect, various approaches like this, for example, splines or what have you. I think it would be a very interesting way to sort of condense our knowledge about how to do these things into a package that is distributable. Okay, one small note that I wanted to make is that the polynomial evaluating this basically order k in the order of the polynomial, while looking up a value in a non-uniform binning is order log n in the bin. So depending on the situation, actually fitting a polynomial may give you better performance. I'm going to demonstrate here that within correction lib, actually it is slower to evaluate the polynomial. So you can see for 10,000 values that I was using to reweight this plot, you can see that the bin correction evaluates in 400 microseconds, whereas the polynomial evaluates in something like 4 milliseconds. But in some cases, like in this sort of toy example, you can see that the inverse is true. So if I do search sorted, which is the basic primitive operation of doing a bin lookup, you can see that it's actually slower than using the NumPy polyval. Okay. So one of the newest features of correction lives is this hash PRNG, and this is for resolution models. Let's say you want to smear a variable like jet energy to simulate the degradation of resolution with respect to what was expected from simulation. Let's say the data has a lower jet energy resolution, for example. If we can deterministically generate pseudo-random numbers, then we can use them after suitable scaling to correct these values. And the reason why we want it to be deterministic is that every time you rerun your analysis, you get the same result. But you would like it to have all the desirable pseudo-random statistic properties, just without the fact that it changes every time you run. And another thing you'd like to be able to do is not have it change depending on the order in which you process events, which is one of the big fatal flaws of using sort of a traditional approach, right? Where you would seed a random number generator at the beginning of the run and then sample from it, but then it depends on the order of events. So you'd much rather have a deterministic pseudorandom number generator where the entirety of the entropy sources that are giving you the pseudorandom number are coming from properties of the event itself. And so that's what this hash PRNG node is for. It's basically a node that takes an arbitrary number of inputs. And so here I'm basically just compiling a various set of inputs that are giving me entropy sources. So like the unsmeared jet PT, the jet kinematics, the event number. And what it does is it uses a extremely fast hashing algorithm to generate an integer seed, which is then used to initialize a random number generator that is designed for high performance with quick seeding. And so, you put all these things together and you actually have something where you will always get the same number out for the same input, but the number has statistical properties that simulate whatever distribution you choose. And there's a few different distribution choices, including standard, normal, flat, and actually a self-implemented normal distribution, because to my great surprise, the C++ standard library random number generator specification does not include a strict specification for how the number is to be generated, only that it's to produce a normal distribution in high statistics. So, Marsalian method versus ziggurat versus the various other ways you can sample from a normal distribution. It's not specified exactly how it's done. So in principle, depending on your implementation, it may change, which is why we have our own custom one if you want assurance that this will always produce the same value on every platform. In my testing, though, I found that it doesn't seem to be varying. So anyway, we can apply this and you can see that indeed, I'm smearing something out. It's not normal here because I purposely made it scale the smearing value depending on where I'm at. But if I were to, for example, just look at the random number generator itself, it should be a perfect Gaussian. Yeah, so that looks Gaussian, at least Gaussian enough. Okay, in interest of time, I'm just going to skip this compound correction. It's basically just a way to simplify applying several corrections in order. And then go to systematics, which is just to say, there are many different ways you can encode systematic uncertainties. Of course, all of these corrections in a real analysis would come alongside with a uncertainty. And there are no dedicated nodes to the task, but we'd love to hear your input on how we could create a dedicated systematic node. There's an issue early on in the development to discuss this. For example, the most straightforward method you can do is just add a new category node type that adjusts how things behave. So for example, in my earlier PT weight example, I could insert a category node called syst, and if the systematic is called muon efficiency up, then I provide a different bind correction value than for the nominal multiplicative event weight. And so that way, this when I evaluate for nominal, it's the normal. And when I do muon efficiency up, I get a slightly different value. Okay. Last but not least, you can compile these into a set of corrections and write them out into a JSON or a gzip JSON. In our tests, we found that actually gzipping JSON, the resulting file size is competitive with basically the file size of earlier formats, even binary formats like root files. Compression works very well, even when you're compressing JSON. Last but not least, for those of you that work in C++, there's a command line utility that provides some useful tools, in particular, including how to generate the necessary flags to compile a C++ program against this library. And just to demonstrate here, I have a simple C++ program where I load that gzip JSON file I just produced and then evaluate one of the corrections. And depending on your platform, you may have to add some extra variables. Linking is challenging, but sure enough, it runs and produces the value we expect. So thanks for your time, and I hope this gives you a nice overview of what the correction library's use case is, and hopefully you find it useful in your analysis and can contribute back and help us build a common language for corrections. Thank you.
Thanks, Nick. This was a super nice talk. So I think we have time for basically like one question. I'll just go ahead and also echo Jim's statement on Slido that that correction light is seems to be a really nice example of a declarative domain specific language. So great work there. And then we have one question, which is the corrections are often affected by statistical uncertainty stemming from the calibration sample size. Is there a built-in way to propagate those?
Yeah, so currently, no, we don't really provide any prescription for how to deal with systematics. I mean, I would include the sample size for deriving a correction as one of the example systematic uncertainties that you would have to propagate. And no, we don't have a currently any built-in solution, but I think it would be interesting to think about what we can do to build that in, especially, for example, in that polynomial fit. For example, you could imagine that tool would not only produce the central value for the polynomial fit to the ratio of event weights, but actually also some sort of uncertainty. That would be a useful feature. But we have to figure out exactly how to do that in a portable and consistent and proper way.
Yeah, sure. Okay, so in the interest of time, I think we're going to move all other Slido questions to Slack. But Nick, thanks again. That was great. And we're now going to close out the session with 2 lightning talks. And so we have another one from Hans on PyHEP MC. So Hans has warned us that he's having a bit of internet connection issues today, but hopefully that will, hold steady for the next 10 minutes or so. So Hans, thanks very much and take it away.
Yeah, thank you. So I hope you can hear me and see my slides.
Yes, quite well.
Okay, good. Yeah, so this is about a recent addition to scikit-HEP, PyHEP MC. It's an interface to the HEP-MC3 library, and the latest version is 2.71, which I just released today. So yeah, it's on PyPI, and you can find documentation and source under the usual links. So the HEP-MC3 C++ library is you can find under this link or this nice paper where it's written up why you want to have this. So basically, it's a library around an ASCII format that people use to store simulated event records. So when you run PyHEP or so, you may want to store the output and put it into some other software. And then a standard way of doing this is this HEP-MC format. And in the library layer, this is implemented in an object-oriented way. So you have an event object, and you have particle objects and vertex objects, and so on. And these are all classes. And you can put some metadata on the run level, on the event level, the particle or the vertex level. So yeah, this is the typical workflow. So the point of this format is to decouple the generator from the back end or or maybe for us it's more the front end. So the detector simulation, or if you want to run Rivet or so, that would be the lingua franca to connect the two. So PyHEP MC is a handcrafted Python interface to the C++ library. It's built on Pybind 11, and it was previously known as PyHEP MC -ng, but then I made an agreement with Andy Buckley, who was the maintainer of this PyHEP MC package that existed since a long time on PyPI, and so now I can use this name. So PyHEP MC was originally proposed for inclusion in this distribution of HEP-MC3, but the authors unfortunately prefer to automatically generate the Python interface with CPP binder, which, by the way, works very well, but it's then automatically generated, just a direct mapping of the C++ interface. So you don't get the nice Pythonizations that this one has. And another benefit of PyHEP MC is also that you can just pip install it. And we provide, as usual in scikit-HEP, we provide precompiled wheels for common platforms. So you can just install it and it runs immediately. And it includes the HEP-MC3 library internally, so you can just start working. So I said that the API in Python is Pythonic. So for example, the C++ one, of course, doesn't have properties. So it uses setters and getters a lot. And these are mapped to properties in Python. The API the API also doesn't give you the native C++ types, but it gives you native Python types wherever possible, and does automatic conversions between the two. And then I also added a very simple I/O with just an open method that is kind of inspired by how Uproot provides an open method to read and write files. And finally, there's flexible import system for the legacy HEP event record. That is what people used in the Fortran days. And for example, PyHEP 6 writes its event in this way. And also working with the authors of the ImpI generator frontend, which provides the data in this format. Some of the nice things you get automatically is the visualization of the event with Gravis, and so the particle library, when you have it installed, also gives you then nice tooltips here in this library, so you and this visualization, so you can just point to one of those particles here, and then you get some extra info like the mass or whatever. And yeah, I told you about simple I/O, so you just import a library, and then you can use this open method. Of course, this is a context manager, so you can just open a file like this, and then you can iterate over the events in that file. And when you have particle also installed, you get great synergies because you can look up the name based on particle ID, for example. So here I just show you what you can do quickly to inspect some event. So this is sorting the particles that are final state in the event record by energy, and it outputs the energy, the particle ID, and the name. The name is provided by particle. Yeah, this is how it looks like. So one liner, it's nice. Yeah, I told you about some attributes. So this is kind of cool. So you can, in principle, add some metadata, and this can be arbitrary metadata almost to the event or the run or so on. So, for example, one of the built-in attributes, so to say, is the so-called run info. So here you can put in information on the generator. Or you can use this feature, for example, to mark certain vertices. So here is an example where I mark all the vertices that have photons as children, I mark as sparkly. And that is using the general attribute system. So I can give these attributes some name, and then I can provide here almost, most of the basic Python types I can add here. So for example, also Boolean. And then I can store in the ASCII format and read out later again, and then work with that. So something I just added was transparent decompression. So this is also something that the C++ library implements, but then you need some extra libraries, and I implemented it using the Python standard lib. So this supports gzip, bzip, and the lmza format. So this is very simple. You just have to provide the right extension here, and then the open method will automatically read this file, even if it's compressed, or you can also write it in a compressed format like this. So summary, PyHEP-MC is a Pythonic interface to this HEP-MC3 library, supports all the formats that this library supports, and also new is that there's full documentation now with doc strings. So you can use help on all the classes, and you get nice docs, and these are actually pulled from the C++ library. And you have these event visualizations in Jupyter, which are really useful. And almost all of the C++ API is covered. Only some minor parts are missing. And if you are participating in the hacker shop, you can actually make this closer to 100% with me. And it's also heavily unit tested, of course, like all my libraries. Okay, that's all. Thanks.
Okay, excellent. Thanks very much for doing a great job of sticking to time, and also it's quite nice to see PyHEP-MC be in scikit-HEP now. So really nice talk. Let's see, we have 2 minutes or so maybe we can see if there's any questions. All right, so I don't see any questions on Slido, so I guess I'll take some chair privileges and just say I think it's also nice, given that since you're using PyBind 11, like you're actually still kind of like distributing the library. So this means that you can, if I'm correct, this means you can pip install PyHEP-MC and also still get the underlying C++, so that if you wanted to still be able to hook in with like Pythia or something else, you'd be able to still direct Pythia to use the HEP-MC3 library that's shipped as well, correct?
That's an interesting point. So that's not how it is done right now, but I mean, in principle, I could do that. So I'm currently, for simplicity, I just compile object files and I don't make a separate library out of
okay.
the
Yeah.
Okay. But I could do that. Maybe it's
that because you have to match the compiler and that sort of things.
Sorry, Henry, can you say that again? I didn't quite hear you.
I said you could potentially run into issues there because, like, if you get a wheel, that you might, that will be compiled with some particular compiler, and you might, if you have a much newer compiler, there could be some issues.
Yes.
Trying to use that as a binary distribution method, which it wasn't really intended to be.
Yeah.
Depends slightly on what you're doing.
Yeah. Okay, so we have one more question and then we'll go to Henry's talk. So we have a question on Slido. For the missing parts of the API, is it possible to drop down into the auto-generated binding seamlessly? I think I know the answers to that, but I'll still let Hans go for it.
I'm not sure I understand the question.
I think that they were, I think this question asker might not be familiar with PyBind 11, but the PyBind 11 bindings are a replacement for these auto-generated bindings. I believe the answer to this question is no, because it's a bespoke craft. Hans has made a bespoke kind of handcrafted API.
Yeah, that's correct.
Yeah. Okay, great. So thanks again, Hans. And let's now transition to the last talk of the day, which is from Henry on what's new with Python 3.11.
Henry is muted. Henry, you're muted.
There we go. Sorry, I can't see my mouse and it's impossible to click the unmute button. Okay. All right. So we'll talk about what's new in Python 3.11. The last time I gave one of these talks was actually what was new in Python 3.8 at PyHEP 2019 in person. At that time, the release of Python had come out, I think, a couple of days before the workshop, because the workshop was in October. This one's a little bit earlier. So this is about to release. The final release candidate came out a couple of days ago, I think 3 days ago. And it is almost here. It'll be coming out October 3rd. There we go. Sorry. So final release candidates available now. The release is coming October 3rd. The themes for this update are, several of them are recognizable. Typing is a theme again. Errors is something that actually was a big theme of 3.9 and 10 and was a really fantastic thing. People loved it, and it's continuing to be a theme. And a new theme, that's just becoming a major theme of Python and will be for the next several years, is it is faster. So we'll start with that one. So the Faster CPython project is in full swing now. It started a year or two ago with Guido van Rossum and Mark Shannon, several people from Microsoft. We got together and decided that they would try to make Python faster, which is a different mindset than in the past, where they weren't worried about making Python faster. So there are lots of different things that went into 3.11, like these zero cost exceptions and things that will change the performance profile. But overall, on average, through the benchmarks that they're running, it's about 25% faster and can be up to 60% faster. So in the plot you see, this is the ray tracing example they have. And you can see the different Python versions being compared, total runtime there, scaled to 1 for Python 3.8. And this is something I think that will be quite exciting both here and in the future. The plan is to just continue this. Eventually a JIT will be added that is planned, though there's just lots of low-lying fruit that were available, like a specializing adaptive interpreter, for example. Most of these things you should get for free, though that may change what you do to get fast code. And there are some features that are added as well, like regular expressions are a bit faster, but if you use atomic grouping or possessive qualifiers, your regular expression will be a bit more limited, but you'll be able to get a much faster match. So error messages was another, errors in general was another theme of this update. This is the error that you'd see in 3.10 for this little piece of code here. And imagine if you couldn't see this first line, this would be really difficult to diagnose because you don't really know what none type object was not subscriptable. Well, in Python 3.11, it now looks like that. So you actually get to see exactly what portion of the expression caused the error. They actually have to store a little bit more information here. This adds a tiny bit of memory, so it is something you can disable with the runtime flag. But it's generally, I think, will be quite fantastic for discovering what's wrong. And like any of these errors, not much has to happen in order for it to be supported. You just get this for free by simply using Python 3.11 instead of 3.10. Now, some things that handle tracebacks are going to have to update, like IPython and Rich and things like that. Okay. Another feature that's added that I'm really excited about is this add note. So exceptions now have an add note method. And if you call that, you can add a note to an exception, and that gets printed at the end. So here, I'm adding a note to the exception and then just continuing with the exception. So this just adds a little helpful message at the bottom. It doesn't mess with the exception. You're not re-raising an exception. You're not, do you chain it together and make your exception way longer? Generally, whatever you do here messes with the original exception. Now you don't have to, and you just have a way to add notes. You can add multiple notes and they'll just stack. It's really, really nice. Again, things like IPython will have to update to support this. Exception groups is actually the only major new syntax feature was related to exception groups. They don't actually have to have the new syntax. The new syntax is except star. So this allows you to handle multiple exceptions, and exception groups allow you to throw multiple exceptions. And this is backported, minus the new syntax, obviously, as a pip install exception group with no S, sorry, ignore the S there. And this actually is really transformational. I didn't realize this until I started playing with caddrs, and caddrs is already using this. And with caddrs is a lot like Pydantic, but you can use just built-in data classes or addrs classes. And when you are trying to structure or unstructure your code, it will show all of the errors at once. So in this case, I was trying to load something from JSON. It had an index, but it was missing. I misnamed the cache v2 and the files v1, and I see both of the errors at the same time. I don't have to run it, fix one error, run it again, fix the next error. They're all collected and showed at once. I think this will be really transformational for certain types of problems. And I said, this is already being used. If you were to use this, for example, in IPython, you would be missing the notes and you would be missing the actual entire traceback. PyTest is another thing that captures and meddles with tracebacks. But I expect that hopefully the backport will be supported everywhere, and that will be supported everywhere as well. Another thing that this enables, this was on hold until exception groups were added, and it was added almost instantly once exception groups landed, was task groups in async.io. So in async.io, you now have support for task groups, which are similar to trio nurseries and several other features you might have seen before, but they are really, really nice. So in this case, this is the entire piece of code, and I have this little lots of work function that's doing some work and also doing a rich progress bar to track it. And then all I have to do is I open up a task group, I create tasks, those run in parallel. And then when you hit the end of the context manager, it'll wait till all the tasks inside finish. So this is what it looks like when you run it. And that's just the output of this exact code. You can copy and paste it and try it yourself if you want, if you have Python 3.11 and Rich installed. So very, very nice. Static typing has just been moving forward a huge amount every release. And there's lots of very nice things here as well. Lots of these will be available through typing extensions, so you can use them earlier as well. Some of the ones I'm most excited for, self-type is really nice. That's such a common pattern, and it's really annoying to do as it is. Unfortunately, it's not supported by MyPy yet because MyPy has bugs, and this really runs into those bugs. And it's MyPy's code, unfortunately, is a bit of a pain. But exhaustiveness checking is one that I was pushing for, and it made it in. So you can just say assert never if something can never happen. Much better than the old weird workaround. Variadic generics was added for NumPy, and that would allow you, and NumPy's planning on having basically the ability to statically type the dimensions of an array using that. And lots of other just nice little features that will make things easier and nicer, like saying required or not required for things inside of a typed dict. Yeah. So a couple more things in sort of the remaining collection of features. TOML, reading TOML files is now built into the standard library. If you're in the packaging world, which I am, this is really exciting. It gets rid of a chicken and egg problem where you need to read your the pyproject.toml to see what dependencies you need to then install dependencies. But you have to install dependency to do that. So that's going away in 3.11. That's really nice. Not writing, just reading. And Python is gaining native support for WebAssembly. So this has heavily been inspired by a lot of the work in PyDide. They've been helping out. But 3.11 will be the first version to actually provide support, only support tier 3, but some support for Python in the browser directly. And then the next version, hopefully, right after October, actually, hopefully this will push up to tier 2 and binaries will start being provided on python.org for WebAssembly. So this will make it easier for PyDide and as well as all the other various attempts to create web distributions for Python. There's a WebAssembly CondaForge project and stuff. Then there's a lot of other little features. Contextlib.changeder. I'm not sure how you would say that together, but the change directory context manager. So you can just throw that in scripts. Don't do it in libraries, please. It's not thread safe. It's just literally just changing the directory and then changing it back. But it's such a handy little thing that you often have to write. Now you don't have to write it anymore. The safe path is something to keep in mind. Python is currently it's opt-in, but Python is providing a way to turn off the looking up the current directory for Python. So things have to be packaged. And be interesting to see how this continues. It may eventually become a default or something. We'll have to see. But there is actually a flag now to tell Python to stop looking in the current directory for things. This is one of the main reasons that we put things inside source directories, by the way. And just a bunch of other really nice things. The limited API stability is still not quite. There's not quite enough there for PyBind 11 to use it, but we've added what we need to Python 3.12. So Python 3.12, we might be able to offer limited API stability API support for PyBind 11. But it's nice to see at least some more things that are really critical, like PyBuffer, get added to it. Okay. So for support, Python's ABI stable as of release candidate 1. We're on release candidate 2 now, which is the final release candidate. CI build wheel fully supports this. NumPy has already started releasing binaries due to the fact that they're using CI build wheel. Awkward Array has already shipped binaries due to the fact they're using CI build wheel, and NumPy shipped them. SciPy is about to release it because they've moved to CI build wheel. Matplotlib, of course, is one of our early users of CI build wheel. They're shipping binaries soon. This is something that has never been done before. NumPy has never shipped binaries during the RC phase, even though you're supposed to. So this really means that more of the ecosystem will be ready on release day than ever before for any version of Python in the past. And GitHub Actions also ships development versions really, really quickly, and that's been extremely nice for testing. So I think this will really help pick up adoption, and hopefully the first release of Python won't have the bugs in it that Python is known for in the .0 versions, like 3.6.0 and 3.9.0 were just horribly buggy due to critical bugs slipping through because people weren't testing. So very excited to see how quickly people pick this up. In the future, Python 3.12 is getting rid of distutils. So it's really important to try to upgrade packaging. I've been working on that. Feel free to watch the Scikit build project that's being rewritten. I have a 3-year grant to work on that. And hopefully that will become a really, really powerful native way to build software. And Unicode is going to be made default in Python 3.15. So whenever you open a file or read text, anything, always specify the encoding as UTF-8. Mostly that is usually what it is, but there are some systems where it's not. And usually you don't want that. If you want, there actually now is a new native encoding, but I don't know why you'd want to use it. I think you should use UTF-8, or if your file is not in UTF-8, you should use whatever it's in, instead of depending on what the operating system is set to. Okay. And that's what I have. Thanks.
Hey, thanks very much, Henry. That was a super overview and in a very short period of time, but that's fantastic. And yeah, like as you mentioned, given the super nice work that you and other people have been doing for like CI build wheel and making sure that there's those release candidates available by default. We have things also like, as you mentioned, the matplotlib is their nightly builds, or including Python 3.11 as well. So I think it'll be really nice to have a large amount of the scientific Python ecosystem be able to take advantage of this right away. Okay, so
there was one question. So somebody asked about the support level tiers, which is a good question, because that's actually, I think, PEP 6 or some very small number, but it hasn't really been very well defined until recently. And this is one of the things that push them into defining it. So, tier level 1 is something that Python fully supports, that if there's a problem, that will immediately break that will be a release blocker. You can't, that system must work. So things like Intel Macs and Linux, the regular Intel Linux and regular Windows count there. So that's tier 1. Tier 2 is something they provide binaries for, and they're a bit, it's not quite as bad. They will probably block releases, but I think it's not absolutely required. It's scaled down just a bit. And then tier 3 is one where they do not provide binaries. It's sort of just at least one developer is trying to help support that system, and they are okay with supporting it, but it's not, if there's a bug, it won't necessarily block a release or anything like that. So WebAssembly is now onto tier 3, which is similar to, it's in the sort of the area that a few of the other kind of strange architectures are in. Tier 2 is where Apple Silicon is right now, I think. And so that's a pretty, the stuff you would definitely recognize inside tier 2. So that would be a really nice place to be. Yeah, that's what that is.
Okay. It looks like that's the only question we had on Slido. So I think that's it for today. So Henry, thanks again very much for the great talk. And that is the last talk that we have for today's second session. So that's it for today. We will be back tomorrow. As a reminder, there is the Thursday Meet and Mingle social time that starts at 10:30 CERN time. And then we'll have our normal session that will be happening in the afternoon, in the European afternoon as well. So we'll see you tomorrow. Thanks very much.
Thanks. Bye-bye, everyone.
Bye-bye.
Bye.